Well, good day to everyone who is joining us today. It's a pleasure to welcome the committee members, the speakers, and the panelists we'll listen to today, other colleagues, as well as members of the public to this online open session of the National Academy's Committee on Attribution of Extreme Weather and Climate Events and Their Impacts. My name is Jim Hurl. I'm a professor of atmospheric science at Colorado State University, and I have the honor and the pleasure of serving as chair of this committee. In just a bit, I will ask the rest of the committee to very briefly introduce themselves. First, I would like to emphasize our expectations for conduct. If we can move to the next slide, please. In particular, the National Academies is always fully committed to fostering a professional, respectful, and cordial environment where all participants can participate fully. All forms of discrimination, harassment, and bullying are prohibited in any Academy activity, including this online information gathering session. Next slide, please. Just a few very brief words about the study. You can read the information on the slide yourself. This committee has been called together to examine current scientific understanding of attribution of extreme weather and climate events and their impacts to climate change, as well as consider user needs and opportunities to improve attribution science capabilities. As such, this study is an important update and expansion of the 2016 National Academy study on this topic. The sponsors of the study are listed on the slide. Please go to the study website by either scanning the QR code on the screen, typing the indicated URL, or simply Googling and allow your preferred search engine to direct you to the study website. Next slide, please. I would like to remind everyone that this is an information gathering session. That is, the committee is in the process of assembling materials that it will examine and discuss while making its findings, conclusions, and recommendations. Therefore, I ask everyone here today to be extremely mindful of the fact that the committee has made no conclusions and that it would be a mistake for anyone to leave here today thinking otherwise. Comments made by individuals, including members of the committee, should not be interpreted as positions of the committee or of the academies. In addition, committee members typically ask probing questions in these information gathering sessions that may not be indicative of their personal views. I also wish to emphasize that today's meeting is one of several opportunities we've had for the committee to gather information as input to the report. Recordings of those meetings are available on the study website, and we have one more information gathering session after today, and that's going to be at a 2-day workshop on impact attribution, the 1st and 2nd of April in Irvine, California. You can also find study updates, upcoming events, as well as provide feedback on the study by visiting the committee's website. Finally, I want to emphasize that the committee will deliberate thoroughly before writing its draft report. Moreover, once the draft report is written, it must go through a rigorous review by experts who are anonymous to the committee. And the committee must then respond to this review with appropriate revisions that adequately satisfy the Academy's Report Review Committee, as well as the Academy's president, before it is considered an official Academy's report. If you have additional questions about the study, please feel free to contact the study director, Stephanie Johnson. Her email is indicated on the bottom of the slide. Next slide, please. This is the committee's statement of task. It's a long statement, so I'm not going to read it word for word. Just to emphasize, we are asked to provide an updated assessment of current scientific understanding and capabilities for extreme weather and climate event attribution. We are expected to discuss the value of attribution science and identify the utility of attribution for different applications. We've been asked to assess current capabilities for the attribution of impacts, examine methodologies of extreme event attribution, including identifying challenges and opportunities for improvement, and provide guidance for best practices. We've been asked to assess the maturity of both research and operational efforts to produce predictive probabilistic forecasts of future extreme events, provide guidance about how to extend the application of attribution science to regions experiencing extreme events without well-established capacity, and to provide guidance for methods to engage different stakeholders with the results of attribution science, and finally, identify research priorities for improving extreme event attribution methods and modeling. Next slide, please. I would like to just have a very quick round robin by the committee members to just briefly state your name, come on to camera, state your name and your affiliation. So I'm going to begin with Hillary, please.
Hi, everyone. I'm Hillary Boudet. I'm a professor in the School of Public Policy at Oregon State University.
Hi, everyone. I'm James Doan from the NSF National Center for Atmospheric Research.
Hi, everyone. I'm Nicole Jackson from Sandia National Laboratories.
Hello, I'm Joyce Kimitai from Imperial College London.
Is it me next?
I'm not sure. Is Al here? I guess maybe Al's not here. Jen?
I'm Jennifer. Oh, sorry. Did I miss out?
Go ahead, Al. Al.
Audio trouble.
Okay. Go ahead, Jen.
All right. I'm Jennifer Marlin. I'm a senior research scientist at Yale University.
Tim.
Hi, Tim Palmer from Atmospheric, Oceanic and Planetary Physics at Oxford University.
Hi, I'm Kevin Reed. I'm a professor and associate provost at Stony Brook University and chief climate scientist at the New York Climate Exchange.
Deepti Singh, School of the Environment at Washington State University.
Hello, I'm Kevin Smiley. I'm an associate professor in Department of Sociology at Louisiana State University.
Tanisha, is she here? And I know Dennis can't make it, so Danielle.
Hi, I'm Danielle Tuma at the UT Institute for Geophysics at UT Austin.
Thank you. And Grace. Maybe Grace has not joined us yet. Okay, so thank you, committee members. I have the pleasure of working with this incredible committee. We're gathering a lot of useful information, and I look forward to working with them to produce this report. Finally, if we can move to the next slide about the meeting agenda today, I just want to briefly walk through this. Today's session is going to include 3 panels of so-called flash talks, very brief 5-minute presentations by the speakers, and then a moderated question and answer discussion. First, starting with speakers on large-scale modeling needs and opportunities for attribution science, followed by a second panel focused on smaller-scale modeling needs and opportunities. And then the final third session today will be on multiscale modeling needs and opportunities for attribution science. To wrap up, before I turn it over to my colleague Tim Palmer to moderate the first panel discussion, just a few reminders about the meeting format. As a friendly reminder, the purpose of this meeting is for the committee to gather information from today's speakers. All attendees in today's meeting are welcome to submit questions to the panel moderators for Q&A in the meeting. There will be both a link and a QR to Slido on the next slide, and I think it's on this one as well, where you can also upvote others' questions that you're most interested in. When you log into Slido, please enter your name so the committee can keep track of who is asking the questions. However, we will need to prioritize questions from the committee during this meeting to make effective use of limited time and prioritize the information gathering purposes of the meeting. If time allows, we may address additional attendee questions after the committee questions. This meeting is being recorded and it will be available in its entirety on the event page in the days following the meeting. So now I'd like to welcome committee member Tim Palmer, who will be moderating the first panel today. Over to you, Tim.
Very good. Thank you very much, Jim. So the first panel is entitled Large-Scale Modeling Needs and Opportunities for Attribution Science. The first panel is focused on these needs, and we're hoping to hear about the strengths and weaknesses of the current generation of large-scale models, or at least the current generation of models which are attempting to simulate the large scales. And the challenges that modelers are facing to improve these models for use in extreme event attribution and opportunities for progress, both in the thermodynamics and in the dynamic approaches to event attribution. So we begin with a series of flash talks from our invited experts and then move to a moderated Q&A discussion. So I'll just introduce the speakers one at a time just before they come on. So the first one is Richard Seeger, and Richard's a climate scientist and research professor at Lamont Doherty Earth Observatory at Columbia University. So Richard, can I pass over to you?
Sure. Thanks, Tim. Thanks, Jim. And hello, committee. Right, large scale. So I'm going to talk about a problem in current generation climate models. It's been there in many generations of climate models that is really getting quite a lot of attention now. And it concerns the changes in temperature over past decades in the tropical Pacific Ocean, and the fact that the observed reality seems to be outside the entire range of the model ensembles. And the tropical Pacific Ocean, we know from the irregular occurrence of ENSO and also from Pacific decadal variability, exerts an enormous influence on climate variability and weather variability all over the world. Droughts, floods, tropical cyclones, you name it, it's influenced by the El Nino Southern Oscillation and fundamentally by tropical Pacific sea surface temperatures. Next slide, please. So if we look at what has happened over past decades, the beginning year here, 1958, was chosen to be the beginning of the ECMWF ocean reanalysis. What we see is that in observations at the sea surface temperature, amidst warming almost everywhere, along the equator, there's been a region that has not warmed, or it's even cooled a little bit. That's the equatorial upwelling region of the tropical Pacific. This is connected beneath the surface to a large region of cooling in the thermocline. In the models, and this is an average over a 14, I believe, large ensembles, you see a very different pattern of sea surface temperature change over the same time frame. In fact, it's been preferentially warming up in the cold tongue region, not cooling. These models do have some cooling in the thermocline, but it's located differently, it's weaker, and it is not connected up to the surface of the equatorial Pacific Ocean. So this erroneous trend in sea surface temperature is going to have serious implications for these models' simulation of climate change. Next slide, please. So what we've plotted here in this triangular plot is the magnitude of the observed trend in color for all start and end dates going back to 1890. So this includes 5 different sea surface temperature data sets, and it includes all start and end dates for trends of longer than 20 years. And what is shaded in is if that observed trend is within the 5 to 95% range of the entire range of large ensembles contained in the CMIP6 experiment, 14 of those. You can see in the observations that a strengthening trend, that's consistent with the West Pacific warming, but the Eastern Equatorial Pacific not warming, is overwhelmingly dominant in the 20th century and into the 21st century. And you can also see that for trends ending in the last few decades, essentially none of the climate model simulations are able to capture those observed trends. This is a discrepancy between models and observations that seems to be getting stronger over time. A signal is emerging in the tropical Pacific that the models are not able to capture. What could be wrong about why the models fail to get this? There have been suggestions it's related to their chronic double IPCC coal tongue bias. There's also been work that we've been doing recently that suggests it might be related to vertical ocean mixing of heat. And there's another line of argument that it's actually the real world is being influenced by Southern Ocean processes that the models are not capturing well. Next slide. So there's another thing going on in the Pacific Ocean, which is Pacific decadal variability. And many arguments have said that the discrepancy between models and observations is just purely a result of natural variability. What we show here in the top left is a trend over the last few decades. And that one is very much influenced by decadal variability. If we run a pattern correlation between that trend and all previous trends going back over time, you see that this pattern has oscillated back and forth. But the forced trend that I'm really talking about here is the one shown on the lower left, which appears over longer periods of time. And you can see that that is a pattern that is just steadily emerging over time. So we think this decadal variability is going on, but underneath it, there is this forced trend, which is a response to rising greenhouse gases, we think, and models are just not capturing that trend. So what are the implications for extreme event attribution? Last slide, please. One is that concerns to tropical cyclones, and committee member Kevin Reed was involved in this work. On the left, you see observed trends. This is actually over the shorter period, and I hasten to add that models actually cannot capture that decadal variability either. And then below it is a trend in observed track density of tropical cyclones. You see like reductions over in the Western tropical Pacific Ocean, strong increases over the Atlantic Ocean. What you see on the right is the climate model mean trend in sea surface temperature, very different pattern, and what downscale cyclone density look like for that. And you can see that it's very different in both the Atlantic and the Western Pacific. What this is saying is that if you had been sitting in 1980 and had the ability to do this projection of how hurricanes would evolve over the next 4 decades, you would have been very wrong because the models just got the wrong sea surface temperature pattern. Top right is another example of what you get for precipitation in the North America sector. For the next decade, had a trend like the observed SS3 trend continued relative to what would happen if the CMIP6 trend happens, which is a warming. And you can see that this represents a drying of North America. It's consistent with a kind of La Nina-like response. So predictions of precipitation, drought frequency over North America will also be affected by this erroneous trends in the tropical Pacific. And finally, just as one other example, East Africa. Models project East Africa to get wetter under climate change, but the reality is that it's been undergoing a long-term drying trend. And that seems fairly well related to that difference between models and observations is another example of something that seems to be related to the models not being able to simulate how this tropical Pacific Ocean is evolving. There are many other examples around the world of extreme weather and extreme climate where model projections will be erroneous because of their errors in representing the tropical Pacific Ocean. That's it. Thank you.
Okay, brilliant. Thank you very much, Richard. I'm sure we'll come back to discuss a lot of this stuff, but in the interest of time, I'm going to press on and just briefly introduce our second speaker, Tiffany Shaw. Tiffany is an associate professor of the geophysical sciences at the University of Chicago, also affiliated with the Center for Environmental Policy at the Grantham Institute at Imperial College in London. And she also works with World Weather Attribution. Tiffany.
Okay, thanks, Tim. I'm going to talk today about kind of building off of Richard's work, talking about how we not only are seeing thermodynamic trends, which we've long appreciated and expected, and maybe are seeing discrepancies in, but now as the signal grows larger and larger, we're seeing trends in atmospheric circulation, particularly at the regional scale. And this is, of course, quite important as we think about extreme event attribution or attribution more generally. How skillful are our models in capturing circulation trends and attributing them to human influence? Next slide, please. So one of the signals we've long expected in atmospheric circulation is a slowdown of the Northern Hemisphere summertime circulation. This is predicted back to at least CMIP3. And over the last 4 decades, you're seeing a time series of that hemispheric average jet stream signal that is in black from reanalysis, the best state estimate we have. This is very well constrained across the different products. And the most recent generation of models in CMIP6, which is the purple, first with the mean in the purple line, shows really good skill, I think surprisingly good skill, with the shading indicating the model ensemble spread. Next slide, please. But it's not just at the hemispheric scale that we see this. We see it if we zoom in over Eurasia. And this is, of course, important because when we think about regional jet streams, this steers storms. This can also impact heat waves as the flow becomes more stagnant. And if we could see, for some reason it's missing, but there's a distribution that is missing in pink, but it's captured a little bit by the dots above, which is the large ensembles. And the most important takeaway is the vertical lines, which are the reanalysis, sit squarely within the spread indicated by the model ensemble that accounts for structural uncertainty and initial condition uncertainty. So we see good scale even at the regional scale. Can you advance the slide, please? Perfect. Okay, but what's surprising to us, or at least to me, is that we've long expected this signal to be due to global warming or human influence of greenhouse gases. But what recent studies have shown is that this signal is actually at least 50% due to anthropogenic aerosols. So this is the unmasking effect of cleaning up the air that leads to warming over high latitude continents. And work in the community has also connected aerosols to changes in heat waves, particularly Schumacher et al. And I think this is a really important thing for the community to consider, that when we attribute not only on decadal timescales but individual events, there's another possible influence from humans that might need to be considered. Next slide, please. So while models show skill in summertime, the Northern Hemisphere, where we might expect the signal to noise to be higher, and there's less potential influence from the tropics, what we find when we look in the Southern Hemisphere in winter, this is an example of a discrepancy. This, I think, really got the community's attention, looking at the time series of storm strength measured by kinetic energy, where the reanalysis, again, our best estimate when we talk about atmospheric circulation, really is increasing much faster than the model mean, which is the black line, and the model ensemble spread showing the fainter black lines. Next slide, please. But a recent revisiting of this by my graduate student, Junsa Kang, has shown that there's quite an uncertain situation here, and perhaps not unexpected. We don't have a really good constraint from reanalysis even of what storms are doing over the last 4 decades. So again, distribution of model predictions in the salmon, individual reanalysis, broadly speaking, going all the way back to, I believe, Mera 1 here, your interim. So we do need more constraints, even from the perspective of the reanalysis. But if you look at the most recent generation, the gold standard of Era 5 or JR3Q, there does appear to be a sense that those vertical lines sit at the edge of the model distribution. And so there is still some underestimate. Next slide, please. And subsequent, deep diving into this has found that this is very much connected to the tropical Pacific that Richard just described. So what we expect interannually when we have a pattern of La Nina is that the South Pacific would exhibit a pattern of low, high, low. This is a teleconnection pattern, but now we're seeing that manifest over the last 4 decades. So this is the reanalysis trend of geopotential height, low, high, low. The colors show the subtropical jet decelerating, and all of these are ingredients for the storms to be stronger. Next slide, please. When we look at the freely evolving simulations, this is just showing the CSM2 large ensemble. We don't see either of these signals. We don't see a teleconnection pattern. There is some small black contours, but they're not in the right phase or the position. And the subtropical jet, which is in the colors, is accelerating in the multimodal, in the large ensemble mean here, as opposed to what we see and expect from a La Nina type of pattern over 40 years, which is a deceleration. Next slide, please. And so as we zoom in and try to understand where the models are going wrong, what we found is if you just go into this coupled model and you correct the sea surface temperature in the tropical East Pacific through this technique of pacemaking, that was used back in the global warming hiatus days by Kosaka and Shea. What we see is by correcting only the sea surface temperatures in the tropical East Pacific, does this pattern emerge in the model, where the sea surface temperatures are free everywhere else. So you see the low, high, low, perhaps not exactly in the right phase, but definitely a clear teleconnection with the coinciding weakening of the subtropical jet. So what this is telling us is our models have a problem with atmosphere-ocean coupling, which of course is not really very specific, but I think it's impacting quite a few signals. And so that's where I'll end. Next slide, please. Is what the community is facing now is a growing number of model observation discrepancies in historical trends. And this is just a recent assessment that we made as part of the WCRP Open Science Conference concept paper. What you can see is it's across many different variables, many different regions. Some of them are connected, we think, as Richard suggested, because by getting the tropical Pacific sea surface temperature pattern trend wrong, this will impact other regions. But we also think there's potentially some very clear issues with atmosphere-land coupling, and then the well-known ones that we have between scales, so convection clouds and radiation being something the models don't do well, and that really feeds into blocking. And so circulation always has something to do with it, but I would say that it's not an external driver, and we have a lot of work to do to kind of piece the pieces together to advance our capabilities in attributing decadal trends, let alone individual extreme events. So thank you very much.
Thank you very much, Tiffany. That's fantastic. As I say, we'll press on without asking questions at this stage, but come back later. So next speaker, Isla Simpson. Isla's a scientist in the climate analysis section of the Climate and Global Dynamics Division of the National Center for Atmospheric Research. Isla.
Thanks. I don't see my slides. Okay, great. You can go to the next slide. So this is, you've already seen two of these panels in Tiffany's presentation. This is just kind of illustrating the range of situations that we face in trying to use our models to represent historical changes. So the one on the left is what Tiffany highlighted, where the kind of overall trend in Eurasian summertime jet stream is sitting very nicely within the model distribution, and we can have some confidence that there's a role for external forcings and driving that change. Of course, it's hard to know the relative magnitude of that in the real world compared to the internal variability. The one in the middle is what's been highlighted by Richard. It's showing the difference in sea surface temperature trends between the West and East Pacific, and comparing the model distribution with the observations in blue. You can see that, like Richard said, the observations are really outside of the model distribution. So we obviously have challenges there in using our models to attribute changes that are related to this. And then on the one on the right, that's what Tiffany also mentioned from her student Junsik, and it's showing Southern Hemisphere storm track trends in a case where really the observations are all over the place in terms of the historical trends. If you go to the next slide, this is just another example highlighting that we also face pretty big differences in forced trends within the models. So this is just showing summertime precipitation over the Four Corners region of the US. And it's looking into the future here, but the point is that these are showing ensemble mean anomalies at different global warming levels in different models. So this is really the forced signal in these different models. And they're really all over the place. So some of them have very strong forced signals, but they don't agree on what that forced signal is, which is obviously a challenge for using the models for attribution. If you go to the next slide. So the point here is that I think this is an opportunity and a need. I mean, we should be able to understand these differences across the models, and in doing so, figure out which ones we think are more correct and trying to narrow down that uncertainty, which will just improve our models overall. But of course, we have to do that for all of the things we're interested in where there is a large spread. Next slide. So this is addressing some of what Richard was talking about, and the potential gains that we can have from moving towards higher resolution. So on the top right, you see observed trends in sea surface temperatures. And as Richard highlighted, models are failing to capture that kind of cooling in the tropical Pacific. But they were also failing to capture the cooling in the Southern Ocean. And on the lower left, as these are initialized predictions. So what you're seeing here is lead year 1 to 5 prediction skill in CSM initialized predictions. And you can see that there's negative skill in those regions, which is kind of aligned with the fact that free running models are not producing or reproducing the trends that we've observed in those regions. If you go to the next slide. So this is now showing prediction skill in the same model, but at higher resolution. So this now has a 25-kilometer atmosphere as opposed to 100 kilometers, and 10th degree ocean as opposed to a 1 degree ocean. And you can see in the difference there that there are big improvements in skill in this high resolution configuration that kind of align with these regions where we know that models are struggling to reproduce the trends. And the same is true in free running simulations with this model and work by Ping Chang and Pedro Denitio that I don't think has quite been published yet. So there's indications, at least from this single model, that if we go to this moderately higher resolution, there might be a lot to gain as we start to represent processes better. But it would, of course, be nice to see that in other models. If you go to the next slide. But it doesn't have to all be about resolution. I think there are other ways that models can be improved. And so this is on the upper left is showing kind of the same one that I showed in the previous slide, the difference in skill between the high resolution and low resolution version of CSM1. But on the right, that's the difference in skill between 2 low resolution versions of the model, CSM2 and CSM1. And so even at low resolution, changes in the physics or changes in tuning are leading to changes in skill in these regions that we think are important that our current models seem to be failing to capture. Go to the next slide. This is just another example from Richard's group showing in low resolution CSM2 that if you flux adjust the model and alleviate biases in the tropical Pacific SSTs, the flux adjusted model tends to give you more of a cooling in the tropical Pacific than the biased model. So there are clearly other ways that we can try and alleviate some of these issues that we're having in reproducing historical trends. Next slide. So here's just a summary. I think we need to improve our understanding of intramodal differences in force signals. I think there's potential to gain a lot from moving towards higher resolution. And I think we could do this kind of in an incremental way. We're now at the place where we can run large enough ensembles with 25-kilometer atmosphere, 10th degree ocean. Now, of course, we want to move ultimately to higher resolution than that. But I think going incrementally, there's a lot to gain. And in general, alleviating climate model biases, I think, is important. A couple of other points that I haven't discussed directly. I think we have challenges when extreme events happen that are totally outside of our model distribution. And we don't know, is that because our models are biased, or is it because we just haven't sampled enough? And so there are some nice approaches coming out in the literature for trying to deal with that. And of course, emulators can probably help with that as well. Thank you.
Okay, thank you, Isla. That's very nice indeed. So we'll move on now to the final speaker, Sonia Senaviratne. Sonia's a professor at the Department of Environmental Systems Science and head of the Institute for Atmospheric and Climate Science at ETH Zurich. So Sonia, if you're there.
Yeah, I'm there. Thank you, Tim, for the introduction. So I will speak about large-scale modeling needs and opportunities for attribution science. And because I was involved in the last IPCC report, coordinated chapter on extreme, and also I'm involved now in the IPCC Bureau, I will have a maybe broader perspective also from this kind of global research perspective. Next, please. I wanted to start by saying where we stand and why we need attribution science. And I think we should say very clearly, we are in a climate emergency and the situation worsens every year. I'm including here a few events of which we know that they have been made more probable because of human-induced climate change. There has been attribution studies about all of those events. For instance, the Los Angeles event, there have been already 2 attribution studies. Next. So I include here basically the cost of those events, so to show that it matters. So for instance, in case of the LA fires, the costs were together of $250 billion. There were 18,000 structures destroyed, 29 deaths, and 200,000 evacuated people. Next, please. In Valencia, you have probably seen the picture of the flooding associated with heavy precipitation. The costs were 11 billion damage and 232 deaths. Next. Then one other event was, for instance, the wildfires in Canada. The total burnt area was equivalent to 4 times the size of Switzerland, or for instance, in the US, 7 times the size of Massachusetts. The total CO2 emissions associated with this event, that's important, I will come back to this, were equivalent to 3 times the emission of Canada. So you see there the potential for further amplifying climate change. There were 8 deaths and 200,000 evacuated people. Next. I also want to mention as a further example, the drought in Europe that happened in 2022. It was the driest summer in 500 years. There was a record burned forest area, and actually there was very high temperatures associated with the drought, which were amplified by the drought. And the total number of deaths was 61,000 deaths. So you see also huge impacts with people dying of this event. Next, please. So attribution science is essential to link causes and effects and allow for accountability and compensations, for instance, in the context of legal cases or climate negotiation. This shows because of the massive impacts that are associated with them. Next, please. So just a few words about IPCC. I think most participants will be familiar with it. For those less familiar, basically IPCC under the UN is developing reports. It has started first in 1990. In the last cycle, the 6th cycle, we had a number of reports that were released. And I will speak about some conclusions of the report on the physical science basis, which I was involved in. Next, please. So in that report, that's the Working Group 1 report, together with Subing Zan, a coordinated chapter on weather and climate extremes. We had authors from all over the world, so across different continents. Next, please. So I will just start with some brief summary of the main conclusions we had. We looked at the range of different changes in climate extremes. We looked at observed change, attributed change, and projected changes. One main first conclusion was that the evidence of observed changes in extremes has strengthened. Next. The important point was that we find from observations that human-induced climate change is already affecting many weather and climate extremes in every region across the globe. Next. And we also found in terms of attribution that some recent hot extreme events would have been extremely unlikely to occur without human influence on the climate system. I think this is important. That's a new era in attribution. In the past, we were rather looking at events that were becoming more frequent, but now we are starting to see events that are so extreme that we can say that without human influence, it would not have really have a chance of happening. Next, please. So here a very short summary of where we find increase in some extreme events, for instance, hot extremes, extreme rainfall, or drought. There was also an assessment of the attribution of these changes, which is shown with the dots, which is not so visible here. Next, please. The main point I wanted to make here is that this assessment was based on literature that was available until January 21. So right now, with some colleagues who were involved in that chapter, we are working on an updated assessment because we have already had 4 more years of events and literature. And there are many more locations where we find basically evidence of observed change or also attributable change. Next, please. So here is actually a direct link to the last report of NAS. That was actually assessment on the right, which was looking at the confidence, sorry, that's very small, in the attributed changes versus confidence in projected changes. And just wanted to say that in the report, we had a basically updated assessment, which was more quantitative. You see here, we have this basically is function of the likelihood language of IPCC. So for a range of different events, what is the confidence in attribution of trends to human-induced climate change and confidence in projected changes at 2 degrees. Really important point is that for some events, I mean, we heard in past talks, there are a lot of uncertainties for some type of processes. But for instance, for extreme heat days or cold days, the evidence is very, very clear, as you can see here. There is also a bit of a change in the ranking in the NAS report. The change in heavy precipitation was considered more uncertain than change in droughts, while in the report from IPCC, actually for heavy precipitation on global scale, the assessment was that it's likely that those events are increasing, while for droughts we were at medium confidence. Next, please.
Are you
Please
almost
start wrapping
done?
up if you can.
Yeah, sorry, I'm wrapping up. Okay,
Yeah.
so I just want to say again, there are, of course, the confidence depends on the type of extreme you are looking at. Next, please. So I have a bit too many slides, but maybe this is just to, it's very similar to, I think, what we just saw before, which was based on a previous paper looking at the change in extreme as function of global warming. And so the mean response is more or less linear and you have some spread. And in this case, the projections are fairly well constrained. Next, please. And maybe you go through again. Next slide. Yeah. Next slide again. For heavy precipitation, you see, for instance, that the uncertainty here was much larger. So the mean response is clear, the sign is clear, but there is much uncertainty.
Okay, can we finish now, maybe?
Sorry, I'm finishing, yeah.
Okay, great.
Next, please. Just going maybe to the last slide. I just want to say that spread analysis, you can check this paper, which was based on 75 data, which is something similar. Next. Next again. Yeah, sorry, Tim. Just want to say last point, there are some modeling challenge in terms of process understanding. For instance, for record shattering events, the role of sun moisture for temperature extreme has been shown to be very important. Here for the Pacific Northwest heat wave, which was a huge jump, it was associated with actually dry condition at the beginning of the event. Next. And last slide. About the uncertainties we heard from Richard, for instance, beginning, and also Ayla and Tiffany, I should say that another area where we find large uncertainties is the relationship between droughts and the carbon cycle. And we find there clearly that models are not capturing a feature we find in the observation, which is showing a strong impact of droughts on the carbon cycle. Next slide. I think that's conclusion. Yeah, just last point is emulators, of course, is also another interesting way to explore the tails of distribution. Thanks for the attention.
Great, thank you very much. Right, I'm going to start because I guess there was some maybe slightly different emphasis, particularly from Sonia. So I want to ask you all, I mean, the first three speakers, Richard, Tiffany, and Ayla, emphasized, which indeed this is the topic of the panel, but emphasized some of the problems that models are having with these large-scale trends. On the other hand, this is the focus on the report is about extreme event attribution, and as Sonia said, these are can be very specific. LA fires and flooding in Valencia, and heat waves in British Columbia. Let's say these sort of things. So my question is, should we care that the models aren't getting the large-scale trends right for extreme event attribution? I just want you to connect the two things together. Is this an issue we should be very concerned about? The issue about not capturing the large-scale trends right. Is this an issue that we should be very concerned about, just slightly concerned about, or not concerned about at all? It's insofar as our focus is being able to make sensible attribution statements about these extreme, typically local weather phenomena. So I'd be grateful actually for all of your opinions, or just say what you think, about this. It may be obvious to you, but just for the benefit of everyone, just say what you think. Richard, do you want to start? You've got your hand up.
Sonia had her hand up first, but...
Oh, okay, fine. Sonia.
Yeah. Well, I think that's what I wanted to show in my presentation, that, and of course there is too much literature to cover, but I guess in IPCC we also focus on where are the areas where we have certainty and where we don't have certainty. And it's important to say is that for some aspects of those events, we have high certainty. So we know with increasing global warming, heat waves are becoming more frequent and more intense. And I would say maybe sometimes there is uncertainty about the quantitative effects. Like I mentioned, in the Pacific Northwest, that was a huge increase in the temperature. But the sign is, we know it's very likely that such events are much more actually. It's virtually certain that they are increasing. So I think for some of those events, it's almost a no-brainer. Still, it's useful to have studies providing the assessment for the single events. And there are some processes for which it's more challenging, like for droughts. And I think what we have seen in Shad's presentation, there are some aspects of the climate system where we have remaining uncertainties. If anything, it's not helping us. So in the case of what I showed at the end, these impacts of a drought on carbon cycle would actually imply a further increase in temperature in the end because you have a release of CO2 associated with it. So it could be even worse.
Who wants to go? Richard?
Okay, yeah. So, Tim, you mentioned the Los Angeles fires, which would be very much a case in point. As you know, burned area in the southwestern United States has been climbing exponentially over the last few decades, and that's clearly related to changes in precipitation and vapor pressure deficit that are clearly related back to the changes over the past decades that have happened in the tropical Pacific Ocean. So indeed, the LA fires, the triggering event was a La Nina that was probably preventing precipitation in the fall, followed by the Santa Ana winds, so some weather, but it's in the background of a climate that has been aridifying for several decades, thanks to the equatorial Pacific Ocean. Now, probably a fair amount of that is the Pacific decadal variability. These models are not capable of getting the amplitude of that. But underneath it, as I was trying to say, is this emerging pattern where the gradient is strengthening. It's kind of La Nina-like, and it's going to have those sorts of teleconnections. So I think in terms of event attribution of a tremendous impactful events like the LA fires, they are sitting within the context of changes in large-scale ocean and atmosphere circulation that are not being captured by the models that we are using for the event attribution. So I hope that sort of illustrates down from the large-scale ocean atmosphere dynamics to an individual extreme high impact event that evolved over 2 weeks.
Thank you. Tiffany or Isla, do you have anything else? Do you want to add to any of that?
Yeah, I mean, I guess I would have given pretty much the same answer as Richard, but one thing to add is that I think, I mean, when we're looking at extreme events, the primary thing that's happening is a shift in the distribution, and that is being governed by the mean changes, some of which might be are thermodynamic, but then others are being forced by these large scale patterns of change that we need to get right. So if we want to be quantitative about changes in probabilities of things, we need to be getting those mean shifts right, as well as changes in the distribution.
Yeah,
Okay.
and I would just like to emphasize also what Sonia said. I mean, we're going to see a variety of different things. So I would hate for us to overemphasize the things our models are doing bad. I think our models are doing good at a number of things. And in those cases, it's just important to distinguish the information and the knowledge. Certainly for heat waves, I 100% agree with her. I think it's quite clear. Now, there are circulation contributions to some of those. And again, maybe that's just what we're refining our understanding. I think what we need to, I think, acknowledge as a community is we don't know what our predictability is. We don't know how good we can be. You know, for numerical weather prediction, it's quite clear what to expect and what the limits are. And what's so interesting or exciting about this time is we're kind of figuring it out in real time, as well as trying to learn what's going on in the real world and improve our tools. We've just never had these signals before on decadal timescales. And so there's a lot of opportunity to improve our knowledge and predictability, potentially.
Great. Okay, thank you. I went slightly off piste with that first question, but I just felt it needed to be discussed. So I'm going to go back on some of the more planned questions. And this one is kind of, it brought, I think the comment that Richard made about the PDO versus the force signal is kind of relevant here, which the question is, to what extent are today's Earth system models able to simulate the extent to which extreme events are influenced by both climate change and natural climate variability? In other words, I suppose, how do we have confidence in being able to distinguish between a kind of a force signal and a natural, let's say, decadal mode? Does anyone have anything to say about that?
I think what is very clear and what's very easily understood is the thermodynamic component. So we know we have more energy in the system. We have increased greenhouse gas forcing, so this is warming up the Earth. And so this means that we have higher temperature for heavy precipitation because of Clausius-Clapeyron. We know the warm air can entail more moisture. So when it's going to rain, you have more total amount of water. But it also means that when you have not reached saturation, more water can be taken up by the air to dry up the soil. So you have also more probability of having droughts and, it's potential for drying. Now, what is more uncertain definitely is the dynamics, and that's can be more dynamics in terms of weather and then also this decadal variability, and definitely there are substantial uncertainties remaining. I would say for me, it's more of a second order aspect for most of the response we are looking at, but it can be certainly relevant for some of those events. So it's important, of course, to have those studies for individual
that's okay.
events.
I mean, that's a pretty important statement you made. So let me just check you've got that right, or everyone agrees with that. I mean, prior to event attribution, I think people, the people would sort of aggregate heat waves around the world or flooding events. And much like you say, they would say, well, the Clausius-Clapeyron relationships mean that, in general, we will expect, to get more heat waves and flooding events just from the thermodynamics. But there was, typically in the past, there was reluctance to attribute a specific events because there was always a dynamical component to any specific event. Now you're saying that somehow you think that even for the individual extreme events, the dynamics is a second order factor. Is that
not for all of them, but I would say for many of them. Basically, I think in the literature, actually nobody has mentioned this so far, but there are two ways to do attribution. You can look at this in a pure statistical way. So you look at the distribution in present and without human-induced climate change. So you would look at the probability of this given temperature in present climate and without the present climate. So this would actually also not look at the dynamics specifically. What you can do also is taking into account that for most of the, change in dynamics, it's fairly uncertain whether we have a force signal in dynamics. There is some evidence that there might be some, I would say, in some cases. But for some of those changes, it's fairly uncertain. So what you can also do is a storyline approach where you prescribe the circulation pattern and then still you modify the background thermodynamics. And so you can basically isolate the two elements. Then I guess you can separate this in two elements, which would be, given the circulation pattern, how probable was this temperature or the dry condition? And the second part is, of course, what is a possible contribution of human-induced climate change?
But there's one question, which is that, or one statement, which I guess is everyone would agree with, that the dynamical response can be uncertain and somewhat linked to the problems that the other speakers have talked about with trends. But it's a separate thing to say that the dynamical effect is relatively unimportant. And I just wanted to get other people's views about that. Do people think that, let's say to first order, we can ignore the dynamics for specific event attribution, event attribution on specific observed events? I don't know.
The question is about the change in the dynamics or the dynamics? I think
the impact that impact that climate change might have had on the circulation patterns, essentially. Do we think that's a second order problem or not?
I would say that if we were to try to argue for where it could be a first order problem, as opposed to knowing quantitatively yet if it is, would be in the summertime and the steering of storms and the slowdown of the circulation, where we unequivocally know that there has been a human influence on the circulation. That is a time when there are a lot of extreme events. And I think the community is still trying to connect the dots. But I would say that if there's going to be a place where we could really dig in And I think this really just comes down to what question are we asking? Like, if you're going into the court of law and trying to kind of argue the quantitative percentages of human influence, I think we're going to face challenges with being able to unravel that because, yeah, our models do show deficient skill. But, you know, if you have a hurricane and it's being steered by a slower flow and it stalls and it has the boost of Clausius-Clapeyron, but more rain falls because it's not moving around the subtropical high. I mean, I think that would be a clear potential place where we would look for a signal. But we don't have, I think, the capabilities of connecting those dots in the literature yet. Maybe that will come online.
I think the
Right.
case that you go.
No, go on.
Well, I was just going to say, I think the case that Richard mentioned earlier about the US Southwest is another example, whether it be forest or internal, we've clearly had a circulation change that has, over the last 4 decades, made the Southwest a lot drier so that any extreme events that come along are in this really dry climate, and wildfire heat and drought extremes are worse as a result of that long-term trend in circulation.
So 2 examples where it absolutely is dynamics. One is East Africa, where there was an attribution study in recent years to a major multi-season drought. They couldn't say a lot in that about how the circulation had changed, but the drought was clearly related to a change in the water circulation over the Indian Ocean. So that's one. Another one is the trends over the past decades in the Mediterranean. Spain across to Italy has been drying much more than any of the CMIP6 models say it should be. That's related dynamically to an NAO trend. The thermodynamic contribution to that is trivial compared to the change in circulation. But what has caused that NAO trend? Is that natural variability? The models don't do it. Is it a forced response the models are not getting for whatever reason? But the event is attributable to the circulation change. We just don't know what caused the circulation change.
Right. And
I would maybe just add one point. And I mean, basically on the IPCC report, and we had an assessment of what is the possible contribution of human-induced climate change to change in dynamics. The assessment is not that there are no impacts, but that majorly it's low confidence. So I mean, we have this superposition of this high confidence signal in thermodynamics and lower confidence signals in dynamics. And I think for single events, it can be certainly determinant. But if you look at, the collection of all events that are happening, especially looking at the qualitative questions, is this more probable now, if maybe not the quantitative aspect, but the qualitative, is it more probable in this climate? Then often thermodynamics is enough to answer this question. If you want to be very precise quantitatively, then you need dynamics.
Okay, I think we should move on because I can see time is pressing. Let me just ask a question. So we've obviously talked a lot about model development. What are the research and model development priorities and opportunities to improve the model's utility for extreme event attribution? Anyone want to take that?
Well, I think Isla highlighted some. I'll just riff off of what she said, but I would like to also highlight that, we need to understand the system in order to predict it better. So while we have all these new tools, AI for scale coupling, AI to emulate the trends, what is it learning and how do we do better? Hindcasts are another great opportunity. Resolution seems to be promising, but as Isla highlighted, there's only one model that's really shown that skill increases as you increase resolution. I think there's a lot of studies that have shown with high-res MIB that you don't see necessarily increased skill. Maria Rugenstein had a paper with a colleague at EGU last year. So I think we need to better understand the system. And some of these like pacemaker simulations where we learn where the models are doing particularly things wrong and relating that, like Richard has shown, to a process will be, I think, the right path, but that's a maybe slower path than on the rapid time scale of extreme event attribution. But I think that's the key, is bringing all these tools together.
Apart from resolution, well, Richard, you had a comment about ocean mixing. I mean, presumably that's not, is that something that's more of a parameterization issue rather than a resolution?
Yeah, I mean, I'm curious about, the high resolution results that Isla was indicating. I don't know whether that included an improved representation of ocean mixing, but I mean, in the oceans, it's very interesting, but ocean general circulation models and ocean reanalyses forced by observed winds still can't get the equatorial Pacific SST trend right. They get the subsurface temperature more nearly right, the cooling, but they don't connect it to the surface. And I think that is because of the vertical mixing. And it's the ocean reanalyses use the same vertical mixing parameterizations as the ocean GCMs, and they're all, I mean, there's a variety of different ones, but they're all in related families. I was very keen to see that, there is a NOAA field experiment coming up in the eastern equatorial and central equatorial Pacific, TPEC-E, TPEC-C, that was going to be doing some serious measurements of mixing that we were hoping to be able to use to better constrain what goes on in the models. I truly hope that in a difficult time for NOAA and the federal government, that research field experiment in the boundary layers of the atmosphere and ocean can actually go ahead in the next 2 years. Because I really agree with Isla and Tiffany that resolution is great and AI methods is great as well, but what we really need is our own understanding of the process. There are physical processes that we are still not understanding well, and just going ahead as we are, hoping that AI or higher resolution is going to solve our problem and everything will be okay, I think is probably a little bit naive, and that we have to go back and think more about the physics involved, and that means going back into the real world with the data.
Is it one or the other, or both?
I mean, I think it can be I think it can be all, but I just want, for the tropical Pacific, we still need more real world data, and we need to be scrutinizing our models, whether they have AI-based parameterizations and whatever resolution they are. We need to be validating them against in situ data.
Great. Sonia, did you have your hand up?
Yeah, I had a few points mentioned. So I had too many slides, but one point I'm very concerned about is one of the last slides I was showing about the drought carbon cycle feedbacks, because there are really cases where actually all models show a systematic bias. So this is one case where we find in the observation a very clear global scale correlations between droughts and the carbon cycle. So whenever on average on land we have less water, we see an additional increase in CO2 in the atmosphere, and which is this correlation is increasing over time, which suggests that droughts are becoming more limiting for vegetations. But basically the models are not showing this. And of course, we know the models have a lot of deficiencies. So I would say, of course, there are many processes we would need to have better represented. But one is biology. So basically, plants mortality is not represented. Plants are not dying when you have a drought in a climate model. I think that's one main concern. And of course, this would have an impact on the carbon cycle. And maybe one point I also wanted to mention about the emulators. So I would agree this is not a panacea. If anything, they are rather a simple version of
very quick, because we're literally
sorry, but where they can be useful is in those cases where models are not doing very well because they could be constrained by observations.
Okay, great. Isla, can you say what you want to say in about 10 seconds?
Yeah, I just wanted to mention the signal to noise paradox. I think that's an opportunity to try and that's something we don't understand in our models on short time scales that we should be able to to understand, that would give us more confidence in our models if we could kind of alleviate those issues.
Okay, that is totally brilliant. Now I'm going to get told off badly by the chair, Jim Hurrell, for not precisely sticking to the questions, but I think you've all done totally brilliantly, and I hope it's been informative for everyone. So I'm going to pass over now to Nicole, I think, for the next next session. So thank you to all the speakers, and we move on to the next session. Thank you. But stick around, by the way, for the final session as well.
All right. Thanks, Tim, for moderating panel 1. So our second panel today is focused on small scale and local modeling need and opportunities for attribution science. Here we are interested in hearing about the strengths and weaknesses of the current generation of small scale models, the challenges modelers are facing to improve them for use in extreme event attribution, and opportunities for progress. Similar to panel 1, we will begin with a series of flash talks from our invited experts, and then we will move on to a moderated panel Q&A discussion. And so our first of 4 speakers today for this panel is Ruby Leung. She's a Patel Fellow and Chief Scientist in Earth Science at the Pacific Northwest National Lab.
All right, thank you very much. So next, please. Yes. So no, sorry, can go back to the first slide. Thank you very much. Yeah. So attributing extreme events requires our ability to represent them in models. And so in this short presentation, I'm going to discuss 2 different examples of using fine scale models to simulate extreme events. One for extreme events that have a large scale context, and then the other where large scale forcing is weaker. Next, please. So here we simulate a compound flooding event in the Seattle area due to a series of atmospheric rivers that produce heavy precipitation, strong winds, and also rain on snow. We use a global model, but with regional refinement that can allow us to get down to 3-kilometer resolution over the Pacific Northwest or the Western United States, so that we can resolve the orographic effects on precipitation, snow, and winds. So here in the bottom of the figure, you can see we are using this atmospheric model to drive a distributed hydrology model, and then a coastal hydrodynamics model, and then an urban hydrodynamics model that get us all the way down to the local scale of 10 to 30 meter. So on the right-hand side, you can see that using this model simulating precipitation for the hydrology model, we can simulate the stream flow very well compared to the observation. And in this particular case, even better than using an ensemble of WRF simulations, which are regional simulations used to drive the hydrology model. Next, please. And then using a coastal hydrodynamics model that you see on the left-hand side, we can simulate the king tides as influenced by the atmospheric rivers, induce storm surges, and also river discharge. And so because of the good simulation of both the stream flow as well as the tides, we can now simulate a realistic representation of the flooding produced by the urban hydrodynamics model, which is shown on the right-hand side. So here you can see that the hydrodynamics model over urban area show a 2 feet of flooding in the Seattle neighborhoods comparable to publicly available reports. And so in this particular example, I show that we can simulate extreme precipitation quite well, and also not only extreme precipitation, but even the impacts of the extreme precipitation on compound flooding. Next, please. And in this second example, I'm going to show some simulations of score lines and derechos. And these are like under weaker large-scale forcing. So here we simulated the 2012 North American derecho using the same global model that I talked about with regional refinement. And here, because an important aspect of derecho is the strong winds, and on the lower left-hand side, you can see that we can use the regional refinement at several resolutions from 6.5 kilometer all the way down to 1.6 kilometer. And simulating winds for that resolution is really important. And you can see as we get down to 1.6 kilometer resolution, the model does much better in capturing the strong winds compared to the ASOS observation, where the observations show that the winds exceeding 35 meter per second. Next, please. So now a question is, how does warming affect the derecho, right? So surprisingly, what we found in this study is that under warming condition, in fact, the derecho get weaker. So as you can see, the areas or the size of the area where we have high reflectivity as well as strong surface winds become actually smaller, and the derecho dissipates even earlier. Next, please. So lastly, I would like to particularly talk about, so the previous two examples that I show are simulating specific extreme events on the weather time scale for attribution. But an important question is how well can we simulate convective storms on climatological or climate time scale for attributing this type of extreme events. So here we compare two year-long simulation. These are the global simulations using the same global model that I talked about before, although this is not using regional refinement. It's a global simulation at 3 kilometers all the way globally. We compare two simulations. One is free running simulation for 1 year, and another simulation where we nudge the large scale circulation towards a global reanalysis. And we look at these type of convective storms and look at the frequency. So on the lower panel, where we show the model biases compared to the observation for spring and summer, we can see that the free running simulation obviously shows some model biases, whereas when we nudge the large scale circulation towards global reanalysis, the biases are significantly reduced. So this suggests that our ability to simulate the climatological features of convective storms can be hampered by the model biases in the large scale circulation, which of course could be traced back to biases that are elsewhere, not necessarily locally in North America. So next, please. So summarizing what I just presented, I think kilometer scale models are generally skillful in modeling extreme precipitation, especially those associated with large scale systems such as atmospheric rivers. So in this case, using a chain of model, we can even get down to very local scale, like 10 meter, to simulate urban flooding due to compound flooding event. And in the particular example that I show for derecho, we see that kilometer scale model can also be quite skillful in simulating these type of severe convective storms. But what I didn't show is that actually the model scale can be quite variable from event to event, and is also rather sensitive to physics parameterizations and also initial and boundary conditions. And also what I show is that the derecho could actually become weaker under global warming, although the response itself although the response itself can also be very variable. And then my last point really get back to the question of not only attributing specific extreme events, but attributing a class of extreme events such as convective storms. So we see that we have challenges in modeling convective storms climatologically because of biases in the large scale circulation, and also for the fact that the response of the convective storms to warming can be quite variable from event to event. So this really presents a remaining challenge in attributing convective storms as a class of extreme events and not just a specific extreme event. Thank you very much.
Thanks, Ruby. And so our second speaker for this panel is Noah Diffenbaugh, the Kara J. Foundation Professor and Kimmelman Family Senior Fellow in Stanford Doerr's School of Sustainability and the Olivier Nomalini Family University Fellow in Undergraduate Education. Noah, the floor is yours.
Thank you. It's a pleasure to be here, and I want to acknowledge my co-authors on the work that I'll show, and Libby will be speaking in the next session and is really the expert on the machine learning work. And I've tried to be responsive to the broad charge to the committee. Next slide, please. And what I'm optimistic about for extreme event attribution is the possibility for machine learning to really accelerate progress. So I'll show some results from a paper from Jared Troke's dissertation here at Stanford. And the 2 points I want to make on this schematic are, number one, in this approach, we are training on climate model simulations, withholding real-world observations. So we train on daily meteorological fields from large archive, in this case in CNIP6, from 2 individual large ensembles. And then we have the global mean temperature as an input variable, and that's the 12-month mean, the global temperature from the previous 12 months. And then once the network's trained, tested, and validated on the climate model simulations, then we use reanalysis inputs to make a prediction of the event given those daily meteorological fields, and we can vary the global mean temperature variable. Next, please. So we've done this for a number of events in the paper, and I think it's important to note that we are very cautious about which events we're willing to go forward with attribution, and that's a key point. There are a number of historical events that this framework performs well for. One of them is this Europe 2003 heat wave, and you can see the composites from the event on the left, and then on the right, you see first the contribution to the magnitude from anthropogenic forcing contributed by the predicted by the machine learning, again trained on the GCMs, and then in this case 2 GCMs, and then using the reanalysis inputs as the prediction. And then on the right, this is the frequency of exceedance of the maximum temperature over the region in the 2003 heat wave when we give all of the reanalysis days as inputs, right? So this is the frequency. If we get the same weather that we've had in the last 4 decades at different global mean temperatures, how often would that 2003 temperature be exceeded? Next, please. So one key result is that the network is not just learning, say, the regional warming, and that's our test of that is shown here. And the summary is that a lot of the attribution signal is driven by the warming, the calendar day warming, but we do see that the network is learning different magnitudes of response to global mean temperature changes for different meteorological patterns. So this was, I think there's a lot more work in this area, but there is information about the physical processes that the network is learning. Next, please. So I also want to make a comment about linking this to impact attribution. And so this is work from Chris Callahan, who's a postdoc working with me and Marshall Burke at Stanford. And what we're doing is taking the results that I've just shown you, that framework, and asking what is the predicted excess mortality from heat using the regression that you see in the upper left. And the key point here is that this machine learning approach allows us to levelize across different global temperature anomalies for the exact meteorological conditions that originally occurred at different global temperature. And you can see that the recent heat waves, which have been had quite an impact, are actually relatively mild compared to some of these older events that occurred at lower levels of global warming. And there's lots of ways in which this basic approach can help us to extend into impact attribution. Next, please. And finally, I just want to note that this framework can also be used for global temperature prediction, including the response of annual global temperature to cumulative emissions, which raises the possibility of linking what I've just shown you with historical emissions in terms of the contribution of different actors to the global temperature anomalies. Next. So in closing, I'll leave these up. I think in terms of the localized predictions, I just want to say that we have work going on to really extend what I've shown into more higher resolution localized predictions, whether that's using higher resolution climate model simulations or using generative AI to make more localized predictions. Thank you.
Thanks, Noah. And our next speaker is Reinhard Schiemann, Assistant Professor of Climate Science in the Department of Meteorology at the University of Reading.
Hi everyone, and thanks for having me. I'm showing slides put together by Ben Harvey and Oscar Martinez and myself at Reading. Next slide, please. And I will show three quite different examples, but I hopefully they all link in different ways to the brief for today. So I will first talk about a new large ensemble and regional modeling that we've generated in the UK. Then have a bit of a summary discussion about blocking in GCMs and show one example about contrast between extreme and very extreme heat waves. Next slide. So Canary is a relatively large UK project. It stands for climate change in the Arctic North Atlantic region and impacts in the UK. And what we are interested is the classical climate extremes, extreme weather from flooding, high temperatures, drought, extreme winds. And on the right here, you see a matrix of extreme events similar to the one Sonia showed in the previous session. And obviously one challenge and one thing we are observing now is that we can sort of, every time we have our annual project meeting, we can update these matrices of events. Now, from the modeling side, like I said, we're interested in extreme weather, and the other aspect is what we call rapid and disruptive change. So that could be a very rapid sea ice decline, for example, or changes in the North Atlantic Ocean circulation. So one thing, in order to run the science project, we realized we need a new large ensemble. Next slide. And that is what we've been working on over the past years, and it has now just come to a finish. The last simulations finished in December. We've been using the Hadley Center model at depending on your context, it's a medium or high resolution, so at 60 kilometers in the atmosphere and a quarter degree in the ocean. And we run it from 1950 to 2100 with historical CMO6 forcing and the SSP37 scenario forcing. For those who are familiar with large ensembles, we used hybrid initialization techniques with 8 macro times 5 micro perturbations. I could talk about that more, giving us a total of 40 members. And we now have 6,000 years of CMIP-like output. And one thing that I also wanted to highlight is that we have produced boundary conditions for regional modeling from this large ensemble. So we have these for a wide range of CMIP-like domains. So large ensembles are obviously not new, but we have quite a bit of output to study weather systems, which brings us back to the extremes that I showed on the first slide. And if we go to the next slide, what we are now in the process of doing is we do targeted downscaling from the large ensemble. So the idea here is that on the one hand, we want to sample climate variability, but we also know very well, and Ruby, for example, showed some examples that the convective scale is very important. So we somehow wanted to bridge that gap. And what we do here is we identify the most extreme UK storms in the large ensemble. So we are focusing on extreme winds on the one hand and on extreme precipitation on the other hand. And then we do a targeted downscaling of the large ensemble all the way to 2 kilometers. And there should be an example on the next slide. So this is ongoing work. So I'm hoping that the animation is coming through. So you should be seeing an intense windstorm that was first simulated on the global model in the top left. And the right-hand plot shows the wind field at 12 kilometers. And we are already seeing some differences, for example, in the maximum wind speed and how the full conveyor belt is captured. And this is ongoing work. We now want to go all the way to the convective scale. So that was my first example, trying to bridge the scale by combining large ensembles and targeted downscaling. Then if we go to the next slide. So a different topic I have worked on over the past years is blocking biases, atmospheric blocking biases in GCMs. And there's here a link here on the slide to a longer talk about this at the CLIVAB workshops that some of you were at or organized last year. And unfortunately, I have no short answer on blocking in GCMs, but we can say a few positive things on the left. So over the last 30 years, blocking performance in climate and weather models has slowly improved, and that's due to a range of things. It's parameterization development, it's increases in resolution in both the atmosphere and ocean. Then I put down, okay, some climate models are now not so bad. What does that mean? We can see really that now the better models in blocking, they're a lot closer to the truth, to the reanalysis than the not so good models. The model spread is still very large. And we also see that model predictions say models agree really well on a slow decline in blocking frequency with a large variability. There are also, and that's on the right, there are also several points for concern. So models continue to underestimate blocking, and there are at least some examples that also atmospheric intrinsic biases remain important. So it's not just SST biases, for example, in corporate models. Again, the spread between the models is very large, and I'm not sure we necessarily understand it. And also we see that model performance is not always consistent. So for example, the model I work with, I know it's very good compared to the pack of all Synopsys models for winter blocking over the Atlantic and Europe, but it's more like a middle of the road model for summer blocking. And I think from everything I've seen, modeling centers are not necessarily sure a priori when they put together the next generation of model, how blocking will perform. So even though we are very much aware of all the different things blocking is sensitive to in models, we don't know how to put it all together to have a good model. So that was my, 30 seconds on blocking. There's more under this link. And then I wanted to show one more example.
Reinhard, can you conclude?
Oh, okay. So the next slide is the last slide.
Yeah, 30 seconds.
Okay, so I wanted to highlight this paper led by Douglas Marone at Graz. And what he did in this paper, so to sum it up, he investigated differences between very extreme heat waves, so talking about a 200-year return period, and heat waves that are not that extreme, with a 2-year return period. And if we look at the climate change signal between these two events, we find systematic differences. But also these differences are different between different models. But we see them in all models, and over mid-latitude land, we see it's related to land surface and atmosphere interactions. So this is obviously a challenge, but also you can derive some conclusions for that for extreme event attribution. And that's where I finish. Thanks.
Thanks, Reinhard. And our last but not least speaker is Janice Cohen. She's a scientist at the Mesoscale and Microscale Meteorology Laboratory at NCAR.
Thank you, Nicole. Some of the questions we look at in terms of attribution regarding wildfires, we're looking at what large-scale factors might influence fire activity, whether it's their frequency, the burned area, the severity, the damage that they cause. Most of the studies you'll see addressing factors controlling fire activity are looking at broad, large-scale factors. That is a broad susceptibility due to higher temperatures or lower humidities. I think some of the critiques we can make of those, these oversimplify assuming a direct relationship between these thermodynamic variables and fire activity. They ignore the dynamic impact on fires. We look at statistical correlations between climate variables and fire activity, and we tend to assume that these are the primary causes controlling the fire activity itself. We also tend to look at climate variability as a persistent linear trend. Like we have this year, next year is worse, the year after that is going to be much worse, neglecting year-to-year variability and decadal cycles, and these give us inaccurate future projections. Click, please. I tend to look at this a different way. Fire growth isn't solely determined by temperature and dryness. We have very hot and dry years with plenty of ignitions where the overall burned area is below average. That's because the variability in the wind patterns, these jet stream shifts, and other large-scale factors that previous speakers have mentioned, these short-term weather events play a dominant role on fire activity. Also, these wildfire events are rare. There are only a few days per year that have weather that can support large fire growth. Only a few % of fires ever get above 100 hectares, and nearly all of the area burned can be attributed to the very largest fires. So I look at this as these extreme events are a combination of different scales. Not only this underlying susceptibility, but the necessity of a 1 to 5 day period of locationally specific weather that can support fire growth, as well as an ignition at the right place and time to take advantage of it. And that leads us into process-based fire modeling. Next, please. If we look at fire activity, we did this study led by Andy Prine, who I hope will jump in and correct me if I get it wrong. If we look at fire activity in California across 8 different regions, let's pick LA since we're talking about the 2025 LA fire outbreak. We can sift through the past and identify days that had these large fire growth, and based on its the fire activity that occurred, we can identify specific fire weather types that in specific locations can drive fire growth. So how do we get these large fires? We have an underlying susceptibility that might be characterized by vapor pressure deficit, and we can identify different fire types in each region that can drive fires. In LA, there are 2 specific, very different types of fire weather that drive fires. One would be the well-known downslope Santa Ana wind events. It's hot. Well, it may not be hot. These can be climatologically cool. They're dry and they're windy. Another type of event that supports large fire growth is weak or no winds, but the temperatures are hot and it's dry. So these are at the opposite end of the weather spectrum, and these drive very different types of fires. We talk about wind-driven fire events where the ambient winds drive fire behavior, or the other type of extreme fires, plume-driven fires, where the ambient winds are weak, but the heat released from the fire generates strong winds that drive the fire. So when we look at historical trends, we can see that in the Southern California, these wind-driven events are decreasing in frequency over the reanalysis period. But we can see and do the same analysis for the climate. We can predict that this trend is going to increase, and these thermal-driven events are likely to increase. And we can attribute these changes specifically to greenhouse gases and human-released aerosols. So not always the climate-driven effect that we expect. Okay, last slide, please. My work focuses on modeling extreme events. We use numerical weather prediction tied to fire behavior models to simulate a broad range of wildfires. I've done over 40. These refine down to a few hundred meters, and we find that if we can capture these winds at these fine scales and include these feedbacks between the fire, we can reproduce nearly all of the distinguishing features of fire events. So I would not say that modeling these complex events, I don't think they're unpredictable anymore. However, we have These scales are an order of magnitude finer than numerical weather prediction is done. There's a lot of calibration or fudging in our field that's a holdover from earlier generations of models, and it's rampant and undisclosed. We have no broad consensus on our model skill or the source of our model errors. So the consequence of this shenanigans in our field are that when poor models don't accurately reproduce an event, you'll see people say, oh, that event was so extreme, it must be due to climate change. Our models can't predict it. This reflects more an inability of these legacy models to reproduce events rather than any change in fire behavior. But we have made tremendous progress in reproducing events and examining attribution studies. For example, the Creek fire was a fire that occurred in weak
Janice,
winds.
can you,
Yes.
it's about 10 or so seconds.
Yes, this fire blew up into a massive mesoscale circulation event. It was attributed to fuel mortality, attributed to climate change, but I can show it was we could reproduce it with the standard vegetation. So, and that anyway, we can, with the physical models, we can test these attribution studies much more than we ever could before. We haven't done a lot of them, but that's active areas of research right now. Thank you.
Thanks, Janice. So now I'd like to invite all four of our panelists to come back on, and we'll take some questions briefly while they're getting the spotlight ready. So a couple different panelists did a great job of kind of showing, I think Ruby had kind of the global patterns plus local hydrology and so forth. Janice had a slide that kind of captured a couple of dynamics plus some of the local information that's needed, and a couple different vignettes of specific types of events. So when simulating extreme climate events, it really does matter to capture some of these small scale processes and that they can significantly influence the outcome of these events. And so to what extent are these processes being captured better today as today's Earth system models move towards a higher resolution?
So
go ahead, Ruby.
Yeah, all right. All right. So I think, again, I mean, I really emphasize two time scales that I kind of try to illustrate. At the weather time scale, it's quite obvious that as you go to higher resolution, you will improve the simulation of extreme events. And this has been demonstrated in weather forecasting for a long time. So as you go to higher resolution, for example, you get better orographic effects and all of these different processes. But the problem is as you get to the climate time scale, then the challenges become bigger, and getting to high resolution helps, but perhaps not to the degree that we hope. And that's because we still have uncertainty in representing small scale processes like tropical convection, and whatever happened in the tropics can ultimately affect your simulation, even if you are only looking at extreme events in the mid-latitude. So I think there are still these type of challenges that are not totally solved by just going to high resolution.
Panelists, any other thoughts? Janice, go ahead. Oh, Janice or Reinhard.
There's tremendous difference across model dynamic cores simulating fire events. It's actually surprising. The model I used was developed for convective scale, storm scale simulations, and it retains sharp gradients and models winds in very complex terrain, and that turns out to be key for representing fire processes. Whereas models developed for mesoscale, it's okay to smooth out the smaller scale circulations without tremendous impact on your simulation. So because a fire starts out as a gradient between a hot fire area and a cool outside the fire area, and we spin up the dynamics from small scales, it's very important in this field.
Reinhard?
Yeah, just to follow on from what Ruby said, and I fully agree. I mean, it's abundantly clear that resolution helps for a range of things, but we also know that it doesn't get us there all the way. I think one thing to add is that at least people like me, we tend to first think about resolution in the atmosphere, but I think we've seen a lot of progress in especially ocean resolution over the recent years. And then again, if I think of topics that I've worked on, like blocking, seems very sensitive to SST biases and to AC interactions, which we do see improve with a higher ocean resolution. So again, that's a field where it's difficult to say where this converges or if we are there yet, but at least the rate of progress seems quite fast, thinking about these ocean models below the 100-kilometer scale.
Okay. And some of you touched on different examples that certainly have their own small-scale processes and interactions, convection, crowd microphysics, surface hydrology interactions, and so forth. And so some of the results that you've shared show we've made a lot of progress, scientific progress, but this question kind of will help us think through what are the ones that are still likely to remain problematic in the near-term future or long-term future? And in this sense, what are the most important model development priorities for extreme event attribution?
Okay. So maybe I'll just try to quickly answer that first. I show some examples, like when you go to higher resolution, it helps definitely, or graphic effects and even like deep convection. As you go to higher and higher resolution, you better resolve these processes would be helpful. But I think it's also quite clear that other processes like cloud microphysics or land atmosphere interactions and ocean atmosphere interactions are quite a bit more challenging. I think partly this is because turbulence essentially plays an important role in these processes, and we are really far from resolving turbulence even using kilometer scale. Like the turbulence that I talk about really affect the atmospheric processes like the mixing and things like that, and the same thing for the ocean as well, right? So the mixing in the ocean is a key uncertainty in how we represent them. So these would have important effects on ultimately the larger scale and the longer time scale.
Do others have any thoughts to add to Ruby's comments? Yes, Noah, go ahead.
Yeah, I think that one of the challenges, particularly for extreme event attribution, is the balance between accurately simulating the physical processes that create the event and capturing enough of the variability to have a robust quantification of to be able to test hypotheses about changes in probability of the conditions that create the event, with the null hypothesis obviously being that global warming didn't play a role. And so I think as we think about model development, including for high resolution local scales, I think we're going to continue to need creative ways to have sufficient, call it sufficient ensemble size, but just that balance that historically has been between resolution and ensemble size. I think we're going to continue to need creative ways, because we can't assume that the physical processes will, that we see at lower levels of global warming will necessarily be the same as global warming increases.
Janice.
I'm actually pretty optimistic about being able to understand and predict wildfire events. And that's because there aren't very many things that are truly important. It's not easy to model airflow at hundreds of meters. It's an order of magnitude finer than we do forecasting, not just because of computational limitations. It's not easy, but it's a rather simple problem. So I think we'll be able to do much better at these attribution studies, investigating the role of mortality that we expect higher global temperatures to cause. And we should be able to give better answers when we look at this from multiple scales, there's a lot of ingrained opinions in terms of what changing climate does to wildfire behavior that we have to work on. But I think there's optimism to think it can be accomplished within the next 5 years or so.
That is optimism indeed. So across the flash talks, there were some exemplars with wildfires, heat waves, derechos. Are there any other examples that you, the panelists, can think of where high resolution models are accurately capturing extreme events and their dynamics at the local scale? And so here we're trying to think about in a much more holistic sense, a broader holistic sense of, and making sure that we're thinking through all different kinds of events. And are there any examples, conversely, where extreme events and their dynamics are poorly captured? And if so, any sort of thoughts on what might be leading to poor model representation?
So maybe just again quickly re-emphasizing that even though I show a good example of simulating severe convective storms, the 2012 derecho, but we actually try to simulate almost a dozen other derecho events, and in fact it's not that trivial to just go to high resolution and be able to be skillfully simulating severe convective storms. So in that sense, I think ensemble modeling could help by perturbing physics, perturbing initial and boundary conditions and things like that, so that we can capture the model uncertainty and at least have the observations be falling within the range from the ensemble simulation.
So
Go
I
ahead,
don't have an
Reinhard.
actually good answer. I don't have a good answer to your question, but perhaps more comment. So one sort of event that I've thought about is we had a very tragic flooding in North Africa. I think it was in autumn 2023, associated with Storm Daniel. So very tragic flooding in Libya, and it's then interesting to think about the whole meteorological storyline that leads to an event. So that was preceded by at least a week of blocking over Europe, and you had upstream and downstream cyclones. So it was an omega block, and then eventually, after quite a long time, the downstream cyclone formed into this what we call a Medicane, sometimes a Mediterranean cyclone, that then moved all the way to Libya and caused this flooding. So there are many different scales and processes involved, and I think almost having a catalog or some examples of this type of events in our mind, and then thinking about what do we need in order to model this, like all of it. Maybe that could be an interesting way forward. I don't know the results that are out there for this particular event, but that's, when you asked the question, that's what came to my mind.
Yeah, and thanks for bringing up a global South example. So we are trying to think of other places around the world where there are these events that happen that we might have historically overlooked. So Noah, yes, your thoughts.
Oh yeah, not hopefully not controversial or surprising, but I think tornadoes are, obviously a high impact event that where there's lots of hypotheses, and the modeling is, remains a challenge for the, for the time and the time scales and ensemble sizes that we need for attribution.
And Janice, I think you kind of spoke to a little bit on even going at a finer resolution towards the back part of your flash talk, of even going to a finer resolution. Any other thoughts on that?
It's challenging. For example, I showed a slide from simulations of the Eaton fire. Some of the wind extrema that both triggered the ignition and contributed to the early rapid spread are wind hotspots that occur in under 1 kilometer in width. These are a few hundred meters wide, and that's challenging from a numerical weather prediction perspective. Also, as we go to finer resolution, I think Ruby would agree that our limits to predictability suggest that the period we can simulate accurately becomes shorter and shorter. I can simulate periods in a fire behavior for a day or two. So we can look at factors that influence that fire's growth, but we don't simulate the event from beginning to end. And that might pose other interesting questions and challenges. Ruby, would you agree?
Definitely, yes. The answer.
And our last question, Reinhard actually had a slide about extreme, the kind of levels of extreme that kind of made me think of this question as well to kind of wrap up this panel. How important is it for a model to be able to model the extremities of an event for it to be useful in event attribution?
So maybe again, I will get started. I like this question, but my answer is kind of yes and no. So I think if the extremities are mainly due to the extremities of the large scale environments, like for example, in the case of atmospheric rivers, if the extremities are because of really high amount of water vapor or very strong vapor transport, and therefore the relationship between the environments and the extreme events is quite well understood. I think it may not be that critical to model the extremities for useful extreme event attribution, because we understand the why we get this kind of extremities. But I think if the extremities are not well understood, then we need to really address this gap first. And in that sense, I think modeling is an important means to help us understand the extremities, and before we can actually attribute the extremities, right? So I really want to emphasize that even though we talk about using models to do attribution, but attribution essentially requires understanding of the extreme events as a foundation.
Noah.
Yeah, I think the key with any event is really to first make sure that we understand the underlying physical causes and diagnose the underlying physical causes. So I think the question of what does a model simulate, potentially for any given event has multiple answers depending on what the ingredients are. I think the 2021 Pacific Northwest heat wave is a great example, and we have panelists on all the sessions that have worked on that event. Certainly for the machine learning based attribution framework that I presented, that's an event where the large scale conditions were so extreme that even training on GCM projections out to 4 degrees of warming, the network didn't really learn how extreme that event should be in the current climate because of the GCMs didn't simulate it sufficiently. So I think a key part of your question is the level of skepticism of the researcher, and I think the skepticism needs to be pretty high, particularly the more extreme the event gets.
And Reinhard, you have the last thought for this panel with about 30 seconds.
Just to explain a bit more why I showed the last slide. So if you, so I remember being in a situation with a student where we looked at a heat wave, an extreme heat wave over China, and tried to do an attribution study. But the observed event was so extreme that basically from all the CMIP models, we had no sampling at all. There was nothing we could actually do because the event was just so extreme. So then a natural thing to do is in that situation, you say, okay, you find an analog, you find a similar event, but you set your threshold lower to a weaker heat wave where you then actually get some sampling in the CMIP models. And the problem with that is, and that's what the paper showed, the Marron et al. Paper, that at least for heat wave, there are systematic differences in the climate change of these very extreme heat waves and the not so extreme heat waves. So the conclusion is, I guess one conclusion is perhaps vary your threshold, look at different sorts of events, and another conclusion perhaps is use large ensembles. But it is challenging. Yeah.
Just
really briefly, Janice.
I think it's important to point out how intensive the simulations we do are, and it's really a challenge to marry them to these large-scale conditions. We can only do so many events, and how do we bridge that gap?
Noah, did you re-raise your hand? I have a little leeway.
I did. I'll add really quickly that I think, you know, I think that the machine learning really does have the potential to narrow this gap. And so getting back to the original question of does the climate model need to be able to simulate the event? I think, you know, in the framework that I presented, I think that, you know, the climate models need to be able to accurately simulate the response to warming, but then, you know, the machine learning framework allows us to use the reanalysis, right? Use the actual conditions of the event. And so I think that's I think in the future, we'll see that increasing as a powerful tool.
And on that note, that was a good note to end on, Noah. I want to thank Noah, Janice, Ruby, and Reinhardt for joining us as part of panel 2. We are going to take a brief break and resume at 1:05 p.m. Eastern Time, where we will reconvene with a third and final panel moderated by committee member James Dunn.
Oh, well, welcome back, everyone, and welcome to our third and final panel. So panel 3 is focused on multi-scale modeling needs and opportunities for attribution science. So fundamentally, when we think about extreme event attribution, we're really asking what's the connection between global scale climate change and local scale weather event. So this is fundamentally a cross-scale problem. And I was pleased in the previous panels that many speakers are already talking quite in depth about this cross-scale and scale interactions and the need for models to capture these scale interactions. And so this panel is going to dig into that a bit deeper. So I'm excited to learn from our speakers about the highest priority science and modeling needs for capturing these multi-scale processes and thinking about numerical modeling, data science approaches, and novel and interesting combinations of the two, all in support of extreme event attribution. So similar to the prior panels, we've got 3 speakers here who provide short presentations, and then we'll launch into a discussion. And for this discussion, we're going to invite all panelists back, so all 11 speakers to the extent they're available, because I think it'll be important to capture the breadth of perspectives you all bring. So let me start by introducing our speakers, and I'll note here that our speakers are all pushing the frontiers in climate modeling and analysis. And so we'll start with Andreas Prine. So Andreas is a professor in the Department of Environmental Systems Science at ETH Zurich. So over to you, Andreas.
Thank you, James, and welcome everybody from my side as well. I will kick us off with a nice image that connects back to one comment that Noah made. This is actually the situation that we had during the largest tornado outbreak in US history, and you can clearly see how large-scale and small-scale processes are interacting. Next slide, please. So since I only have 5 minutes, I give you my key messages right away. The first one is that extreme events really arise because of an interaction of phenomena across scales. This is not the exception, this is really the norm. The second point that I will show you an example for is that we truly need quite high resolution models to simulate those interactions between scales. Next. So in this study, what we were interested in was, like, given very heavy rainfall events, actually the most heavy 100 rainstorms in each of these IPCC regions that you can see here in these hexagons, we wanted to know which phenomena is causing this extreme event. So if you click one more time, we will zoom in on the Eastern North American region, just for an example. And what you can see here, out of this 100 events that we looked at, all of them were connected to mesoscale convective systems. This is basically organized convective storms, which is maybe not surprising. But additionally, 70 of those events were associated to frontal zones that were close by. 50% had a jet stream close by. Also 50% were close to a cyclone. A third of those were cutoff lows. 10% were tropical cyclones. And then maybe surprisingly, 40% were close to anticyclones. And this is maybe something that many of us don't relate to extreme rainfall. And 40% were close to atmospheric rivers. So you can already see this interaction between phenomena across scales really importantly. If we look next, this is a nice example here. This is Hurricane Florence, that made landfall over the Carolinas in 2018. And actually stalled there when it made landfall. And one of the reasons why it stalled is because there was this big anticyclone that you can see here north of it. So basically the anticyclone blocked the cyclone from moving out of the wave, moving northwards and eastwards, and then it stalled in the location. So a nice example for why these interactions are really important. So next I wanted to show you, oh yeah, and of course, like I think these interactions are really key because I think of those as multiple dice that you roll, and you really have to get all the processes aligned across scales to create an extreme event. And this is actually exactly the reason why they are rare and extreme, because you have to align processes along across a quite large scale of ranges. Next. So I also wanted to show you an example where scale interactions were really important. This goes back to Reinhard. What you see here is a convective outbreak in the US creates a very amplified Rossby wave that you can see here. It hits Greenland later on. Now we have a warm conveyor belt embedded there, and then it breaks anticyclonically. So this led to a quite heavy atmospheric river making landfall in Greenland and transporting a lot of moisture into the Arctic. Next, we can look at the key points in this development, in this forecast. First one, this is from ERA 5 actually, so this is reanalysis data that we're looking at here. You have this very strong convective outbreak over the eastern US. The red colors are basically showing you negative potential vorticity or large diabatic heating. Next, if this convective outbreak is deepening this wave, then a warm conveyor belt develops that further increases latent heating and deepens the wave. And lastly, next, the wave is breaking anticyclonically. Next. So you can see quite a lot scale interactions here. And it's maybe also not surprising that none of our global forecast models was able to simulate these events. And this is quite typical for these kind of situations. GFS, for example, had, as you can see here, a cyclonic breaking wave rather than an anticyclonic breaking wave. Also, IFS wasn't able to simulate this event. And we were basically reproducing this result by using a 60-kilometer MPAS simulation and model for prediction across scale. And we basically didn't get the deepening of the wave either. So what we found next, you really have to go to quite high resolution to simulate the amplification of this wave in the first place. So 3.75 or 15 kilometer was at least necessary to get the deepening of the wave. But then the anticyclonic wave breaking was even more difficult to simulate because we saw that there are different trajectories. You really have to simulate a secondary ridge that is in the east. You can see this over the US at the moment where the thunderstorm is. So you need the second ridge and another convective outbreak. And what this does, if we do next, this convective outbreak, if you simulate it correctly, is weakening this cyclone that is on the east side of the ridge. Next, so it's getting weaker. And only the members that had this convective outbreak next led to this anticyclonic wave breaking that we actually observed. And none of the other members were able to simulate the anticyclonic wave breaking. This goes back to Reinhard's point earlier. So the blocking and these kind of amplified waves that we often see under extreme events are really difficult to simulate. And I think our global models and also the forecasting models that we have are not really able to do those at the moment. And the high resolution models definitely have a large potential to resolve many of those issues. Next, so I just wanted to close with my main conclusions again, and I'm looking forward to the discussion at the end. Thank you very much.
Fantastic. Thank you, Andreas. That was a powerful example of cross-scale interactions, not just downscale, but upscale too. A real challenge for our models. Okay, great. So let me welcome our second speaker, Ben Kirtland. So Ben is a professor of atmospheric sciences at the University of Miami's Rosenstiel School of Marine, Atmospheric, and Earth Science. So over to you, Ben.
Thank you. So following the previous talks, I just want to start with the three takeaway messages that I want to highlight. Please ignore the typo in the second bullet. The first point I want to make is that to think about predictability of extreme events, whether that be on subseasonal to seasonal decadal timescales or whether that be in a climate change environment, you really need to have tools that capture the large-scale climate drivers. So the large-scale climate drivers set the stage for predictable regional extremes, and I'll show you an example of that. The second example I want to talk about is, or to think about that I'm thinking about is that we put a lot of effort into resolution. We need to think about how we put that resolution in for critical processes. So we need to understand why we need to resolve something. So just throwing resolution at something doesn't necessarily make sense. And there's been some discussion that understanding has to underlie why we're increasing resolution in certain regions and certain places. So it's really important to think about resolution for critical processes, not just for the sake of resolution. And then the last point I want to make is that there's really important upscale effects associated with some of these regional extremes and these regionally resolved processes, and getting those upstream effects it is going to ultimately require, global models to capture some of these things. So we are going to have to push the envelope on resolution, but where it makes sense, and we're going to have to do that at global scales. So next slide, please. So the first example I want to show is just thinking about, fire in the West has come up a lot. And so this example is actually focusing on a fire that happened in my hometown, right near my hometown. It was the mountain fire right near Santa Barbara. The top panel is looking at the large scale environment structure of the large scale environment. This is actually surface winds, but the large scale environment that an extreme wind event is embedded in. So the top is observational estimates. The bottom is trying to predict that observational pattern 3 weeks in advance. And so what I want to argue here is that if we can predict these large scale patterns reasonably well, then there's a chance of capturing the very high resolution, very intense winds that were associated with the mountain fire. Next slide, please. And so what's popping up here is a 500 meter resolution of the mountain fire that I mentioned previously. The fire extent is shown there. It's a 2 by 2 degree grid that's trying to capture the extreme winds right at the peak phase of the fire. So this is 18 hours in. The boundary conditions for this is the critical aspect, the boundary conditions for this simulation come from the 3-week forecast. So not from observations. So I'm using a forecast to drive that very high resolution wind event. So we might have been able to predict that there was a big fire risk, not just on this large scale, but on some regional scales. Next slide. The next one I want to bring up is this question of resolution. And the one I want to pick on is actually resolving ocean eddies. And we saw some earlier results from the first panel that talked a little bit about resolving ocean eddies. And I want to just show you some examples of some seasonal forecasts. These are actually real initialized forecasts with an eddy resolving ocean model. And we're looking at periods where the Kuroshio and the Kuroshio extension is highly active, where there's lots of eddy kinetic energy, and periods when there's relatively low eddy kinetic energy. So high EKE and low EKA. Next slide, please. And so this plot is just showing you the vertical velocity right over that Kuroshio extension from the high resolution model. That's a 10-kilometer ocean coupled to a 25-kilometer atmosphere. And the arrows denote rising or sinking motion. And the bottom panel is showing you for those exact same set of forecasts. It's a fairly large number of them. The exact same of forecasts, the low resolution model. So the atmosphere and the ocean are talking to each other in very different ways in that eddy-rich region. Next slide, please. The critical element is downstream. When you look at rainfall in California, the top panel is showing you the observed rainfall anomalies associated with the active minus inactive periods. The middle panel is showing you the high resolution simulation. C is showing you the low resolution simulation capturing those active minus inactive periods. But it's the cumulative distribution, the last column, that I want you to focus on your attention on. And what you can see is you get a big change. The model is detecting very different rainfall patterns associated with active and inactive periods that is not captured at the low resolution model. So ocean eddy processes pumping moisture in the boundary layer, propagating downstream, affecting rainfall in the Western US. Next slide, please.
Can you start to wrap up soon?
Yep. So last 2 slides here very quickly. This is looking again at ocean eddy resolving. This is looking at how teleconnections associated with decadal scale variability in the Southwest US rainfall patterns, how observations indicate the importance of the Atlantic. The second panel is showing that high resolution model captures that, and the CMIP5 models don't. And just last slide, forward one. And so it's that upscale influence of the Gulf Stream influencing the North American subtropical high that's affecting rainfall, and low resolution models can't capture that Gulf Stream effect. So they miss the upscale effect and they get the wrong teleconnection patterns. And I'll stop there.
Great stuff. Yeah, thanks, Ben. I think you made a great, powerful point there that we're not just throwing resolution at the models, we're doing it in a way to understand processes so we can be intelligent about it. Okay, well, on to our next speaker, Elizabeth Barnes. So Elizabeth is a professor of atmospheric science at Colorado State University. Over to you, Elizabeth.
Thank you, James. So I'm going to talk briefly here. I was asked to speak about AI and deep learning development for Earth system prediction and attribution. So next slide. At this point, we've all heard quite a bit about AI, and I just want to point out that it has many, many uses that could be applicable to attribution studies. So for example, we've already heard about making specific forecasts and getting the processes right, for example, in severe hazards forecasts. Next. Also, AI is being used for post-processing of other data sets or AI data sets, specifically, say, compression, downscaling, etc. Next. AI is also, next slide. AI is also, oh, that's okay, it went double. AI is also being used to improve models. This is some of the first ways it's entered into our field. So how do we make our dynamical models better, not just faster? Next. Also, I think one of the huge benefits of AI is the ability to merge different data sets. So for example, wanting to take both observations and dynamical model output or AI model output and combine them together to create one final, say, forecast prediction emulation. And I think this has been a challenge for our field for quite a while, and AI tools may allow us to do this more seamlessly. Next. And finally, I just want to point out that deep learning emulators, so models that are purely data-driven for weather and climate applications, are really exploding. This is just a short list of the models like this that came out at the end of 2024. And here's a nice video from NVIDIA showing on the left an AI simulation, on the right the ERA 5 ground truth. So I think one of the things I want to talk about in my final few minutes is how we might use these emulators for attribution studies. Next slide. So some new frontiers. First, I want to point out that deep learning for extreme event attribution is already being attempted. It sounds like you've already heard of some examples, like from Noah Diffenbaugh in the upper right-hand corner, but there are other papers that have come out in the last 6 months specifically using these two from arXiv, using AI emulators for attribution. Next. They offer very quick and low cost, and by low cost, I mean after being trained, which can be really helpful, for example, for large ensembles if you're doing uncertainty quantification. So here's a really nice example of a huge ensemble. All those blue dots are a different member to simulate a particular extreme event in Kansas City. And you'll see that the red dots are or red triangles are the IFS, and then the blue, the argument here is these hens, these huge ensembles driven by AI emulators can span a much larger space and capture what actually occurred. Next. And finally, just to point out, this is just in the last few months, but coupled AI emulators. So not just of the emulators of the atmosphere, but deep learning emulators of the coupled atmosphere-ocean system are just starting to come out online and run stably, which are going to be particularly important for this application. Next, for attribution. Okay, so I think I want to end with some really important questions. Are these AI emulators and models fit for purpose? And how will we know? So unlike weather forecasting models, the models we want to use for attribution studies need to be credible when external factors are very different from history. And this poses a huge challenge for purely data-driven emulators. Next. And so one of the questions we have to ask as a community is, how do we know when they are failing and when they're fit for purpose? And I just want to point out, often in dynamical models, especially when we think about attribution, we talk about things like model drift. And I would like to show you that these AI emulators suffer from the same problem. So when these emulators are used in a warmer climate, which is that top line, or in a cooler climate, which is the bottom line, they tend to drift back towards the state they were trained in, which is the present day. And this has major implications for attribution applications. Next. Furthermore, they really learn from the data that they are trained on. So this is a really nice example of an AI emulator that 10 days after initialization of an idealized no topography baroclinic wave test. And what your brain may not think this looks weird, but I said no topography. But if you look at these two forecasts, you'll very clearly see the outlines of continents. And that's because these AI emulators, this particular one, was trained on data with continents, that is a reanalysis product, and so it automatically adds it back in. Once again, showing that these out-of-sample applications, which I think in many ways attribution studies will need to be able to do, poses some challenges. Next. And so just in my view, for 3 priorities for these deep learning applications for attribution. 1, we really need as a community to identify rigorous evaluation of these emulators. We have to agree on what tests are necessary as well as how to implement them, and we have to do it. Number 2, assess and understand how these models behave under realistic climates that are out of distribution. And I really think many of them will fail. And one of the things I find scientifically fascinating is when they do fail, what strategies do we have in place to improve their performance? These may be different strategies than we've used with our dynamical models. And finally, one thing I think that's really promising about these tools is they allow us, as I already mentioned, to leverage a wide range of data sets to potentially support the full pipeline from Earth system simulation all the way to some final impact that we're interested in when we talk about attribution. And that's been quite challenging in the past, and maybe they offer a way forward. So I will end there. Thank you.
Great stuff. Yeah, thanks, Elizabeth. I feel like that could have been a 2-hour seminar. Sorry, we only gave you 5 minutes, but hopefully in the discussion, which we're moving on to now, there'll be time to dig into a few of those thoughts a bit deeper. So now I'd like to welcome all speakers back. So Ben, Andreas, and Elizabeth, but also Richard, Tiffany, Isla, and Sonia from panel 1, and Ruby, Noah, Reinhard, and Janice from panel 2. That's if people are still available. Okay, so for some of these questions, I'm going to give priority to the speakers we just heard from before opening this up, so we get a chance to hear from them also. So let me kick things off. Before I do, a reminder for everyone to input questions into Slido, which I'll be monitoring. So over this panel and the prior 2 panels, we had a lot about which scales might be important. There was some argument that we need to get the large scale drivers correct as a first order, but then for some problems, maybe we need to get the fine scale, 100-meter scales correct. So I wanted to throw it out there. Which scales or scale interactions are most important to get correct in models for attribution science, and what might that depend on? So I'll just open it up to the 3 speakers we just heard from first. Andreas.
Oh, Andreas can go, sure.
Yeah, I'll make it quick. Like, I think it depends on, like, if you think about this as a downscaling experiment, then of course the large scale is really important. But if you have some interaction between small scales and large scale, then of course getting the whole chain correctly simulated is important. And I think the later is more often true than not. So really having a realistic representation. Then of course the question is, how fine do you have to go? Like, do you really need large eddy simulations globally, or is it okay if you start with simulating deep convection realistically, or ocean eddies?
Thanks, Andy. Ben.
I think Andreas nailed it. You know, if there's upscale effects, then you're not going to get the large scale drivers correct either. So in many cases, we need to be really careful and understand the processes we're trying to get right at the regional level, and what do we need in order to get that right.
Processes, yeah. Okay. Let me open it up to everyone for any comments on scale priorities here, or scale interaction priorities. Okay. Well, let me broaden the question then. Another question about priorities. So we just talked about the importance of process-based understanding, but thinking generally, where would be the highest priority among improved model physics, improved model resolution, or improved better defining what the observations say about the real world? So better formation of observational constraints. Wondered if anyone had any thoughts about that. If you had a year's 12 months of research to focus on one of these things, what would it be? Noah?
Yeah, I might answer with a slight non sequitur that maybe is applicable to the previous question as well. I think this question of impossibility that's come up is really important, and both for understanding how the world works and for a lot of the reasons that society is interested in attribution. And so that question might be something for the committee to consider that might help to answer these prioritization questions.
Ben, I think you were next.
So I would be reluctant to prioritize one over the other. Instead, I would be thinking about what type of extreme events we need to be able to get our hands around, be able to attribute or to predict. And then I would ask, what do we need in order to do that? Do we need more and better observations? Do we need more and better resolution? Do we need better model physics? So that's the way I would approach it, is from what phenomenon are we trying to capture, what processes need to be represented, and what observations need to be taken to understand those processes.
Yeah, there's this notion of sufficient models, sufficient resolution, sufficient processes.
Exactly.
Sonia, please.
Yeah, I would have had actually a similar answer. So to me, we are at different levels for different type of extreme events. I tried to convey this also based on the IPCC assessment. So, I mean, in the end, the question of attribution is, can we say that this event has been made more probable because of human-induced climate change? And for some type of extreme, it's rather trivial. So we know, again, for heat waves, it's trivial. Temperature has been increasing everywhere. Now, quantitatively, you could have, and that's also what Reinhard was showing, that for very extreme heat waves, and I also mentioned it for the Pacific Northwest, for instance, there, so much temperature feedback may play the role. So if it's really important for you to explore this tail of the distribution, then it will be essential to capture this type of process. So in the end, it's also which question you're addressing. Now, about, for instance, high resolution, and also, representing this very high resolution processes. Obviously, it was mentioned about tornadoes. I mean, that's an area where we have still very high uncertainty, also severe convective storm. We cannot really nail this down. Also in the IPCC report, we said there we have rather low confidence. There, observation seems to show a trend, but it's not clear enough to. And there is also an issue with availability of data. So I would say in the end, it depends on the type of extreme you're looking at, and also which type of question you're asking for each type of extreme event.
Exactly. Andreas?
I had a similar answer to Ben, and I think I would be also reluctant to separate dynamics from physics, because if you increase the resolution of the model, you probably also want to adjust the physics. And this is also something we don't know very well, like how we adapt the physics, depending on what often you run physics that are not really developed for your model. And maybe one comment here is that connecting to numerical weather forecasting community could help there as well, especially if you think about these convective storms and things like that, where they have a lot of experience with developing mesoscale models, physics, like the microphysics turbulence schemes. So those could be really helpful, and also learning from weather forecast biases busts, for example, where you also see that certain situations are really hardly predictable and hinting towards systematic biases.
Yeah. I'm going to go to Richard and then I'll go to our committee member, Tim. So Richard.
Yeah, I'll definitely go with everyone else on an all of the above approach, but to get to the issue of the interaction between the scales, sure, that's fine, that's great for the extreme events, but if we're talking about going back to panel 1 and the large scale processes, large scale dynamics and problems that models are having, if we consider what I was talking about in the equatorial Pacific Ocean, the fact that the models can't get the observed cooling there over many decades could be related to their inability to get right the meter scale vertical mixing, both at the bottom of the mixed layer and between the mixed layer and the thermoclines. So although that's a very fine scale process, it could rectify up to very, very large scale. And through that, the global atmospheric circulation and how extreme events are distributed around the planet. So that's a good connection. And it's also the case that we don't really have good observations of what that mixing is. This is a huge term in the heat budget in the upper equatorial Pacific Ocean, and it neither seems to be well represented in ocean reanalyses nor ocean models or climate models. So there's a need for more observations of this, a need for working out how to better connect those small scale mixing processes with the large scale, and whether that can be done with improved parameterizations, or is it going to require AI-enabled parameterizations, or whether it's going to require much higher resolution in the atmosphere and the ocean.
Mm-hmm. Yeah, quite the challenge. So briefly, I'm just going to go to Tim, and then we have a compelling question on Slido. So Tim Palmer. Oh, you're on mute, I think.
Yeah. Sorry. I realize I'm slightly butting in, but I just want to ask a question. It's kind of a little bit motivated by Sonia's comment, and it was also a comment in the earlier attribution report by the National Academies that kind of heat waves are somehow easy to attribute. And the issue for me comes around some of the things that Reinhardt mentioned, because heat waves, I mean, certainly the 2003 heat wave over Northern Europe was very much associated with a persistent blocking anticyclone, and indeed the British Columbia heat wave was as well, a persistent ridge. And as Reinhardt said, these persistent anticyclones are very difficult for models to simulate well. So, if we think that there is a dynamical component, that climate change could alter the frequency, maybe make them more likely or maybe make them less likely. That seems to me is a relevant factor then in, for example, knowing whether these heat waves will become more prominent in the future, specific ones. If the circulation changed in such a way as to make the anticyclones less common, then the heat waves would become less common, the thermodynamics notwithstanding. So I guess the issue for me is I'm not quite clear in my mind. I appreciate comments from anybody that heat waves are actually easier to attribute than any other event because again, the dynamics seems to me rather non-trivial.
Okay, I think Noah was first up.
I'll let Sonia go first.
No, you were first. You go first.
Okay, I think as with a lot of these attribution questions, like what is it that's being attributed is a key question, and even for something as defined as heat waves. So I think that, and I hate to keep coming back to my 5-minute presentation, but if we look at something like the frequency of reaching a threshold, right? I think that we're seeing already with as much global warming that's happened that meteorological conditions that would have produced a less severe heat wave in the past are now, in many cases producing a more severe heat wave, which now actually we're getting frequency of what used to be much more extreme becoming much more common for a collection of different meteorological conditions. So I think for the question of the frequency of exceeding the surface conditions, the temperature over a station or over a region, I think that's one category of attribution question where we have, much clearer, where it's much more easy to say, we just have higher confidence even before running the analysis that the probability of reaching that temperature has increased. I think for your question of these really for the specific event, and I think actually comparing the 2003 European heat wave with the 2021 Pacific Northwest heat wave for our particular configuration with this, training on the GCMs and then using the machine learning to predict, the network is much more accurate at predicting the 2003 heat wave conditions from the reanalysis than the Pacific Northwest heat wave. So that actually might be a way to ask the question of what that you're getting at, one of a number of ways. But I think for severity of specific conditions versus frequency of a historical threshold, I think you're probably going to get different answers to your question.
Yeah, I think I would have said something similar. So again, in terms just of the frequency of those events, they have become much more frequent. And also some events are so extreme, again, without taking into account the thermodynamics, you cannot explain this. But of course, you have additional dynamics factor. And maybe there I would take a step back and say, okay, what are we trying to do when we do attribution? And in a different context, this has been used for was, for instance, in legal cases, in the case of tobacco. Yeah. So basically, one question that was asked in the past was, if you are smoking, does this increase your chance of getting cancer? And I think the science now is very clear, and most people would agree to say, yes, smoking will increase the probability. Now, in a single person, maybe with a terrible cancer, who has been smoking a lot and doesn't get cancer, you have always these individual elements. And that's also super interesting to understand why one person will not follow the general statistics. But we need to keep in mind that there are different questions. One is about saying, are the probabilities for this type of event higher now than in the past? And therefore, heat wave is very clear. The answer is just yes. But then maybe to answer the question, why was this event so hot? Or why actually, despite those conditions, we didn't get such an extreme event? That's a different type of question. And one doesn't exclude the other. And again, it's about in which context are we using attribution science? And we say a lot of the application is actually a social context, is to answer this type of question of legal cases, basically negotiation between countries. But there is a physical understanding. Don't want to say this is not interesting and not useful. I mean, it's super interesting also to follow this up.
Okay, thanks both, and thanks Tim for the question. It was important to dig into that. So now I'm going to switch to Slido. There's a couple of questions that have come in that are coalescing around a theme. So I'm just going to ask one of them. And I'm just going to speak it verbatim. So attribution, as in Pearl's causal inference, requires a counterfactual. So the question is, how do you train AI emulators on a counterfactual? So I'll throw that open. Libby, yeah.
Yeah, I think there are lots of ways to do this. Maybe I can highlight just two ways. I think Noah's already talked about one method that his student used, which is, first of all, training on climate models to sort of span a range of the ability to predict a range of climates. And in that particular case, having the dynamical fields be anomalies. And so in that way, you're sort of trying to first remove the climate change part, and then you input sort of where in the climate system are you? That is, like, what's your CO2 level, for example, or what is the global mean temperature as a metric to quantify the current amount of anthropogenic forcing as an additional input. And so then what the AI is learning to do is to link up the dynamics, the anomalous dynamical patterns with some amount of CO2 or some proxy for that. Now you might say, well, why just CO2? Why not some other anthropogenic forcing factor? And the answer is you would set up your problem differently if you wanted to do attribution for like anthropogenic aerosols, for example. That's one methodology. Another way, and this is more on the emulator side, is when we're training emulators, we're really trying to learn the physical system in exactly the same way that our physics-based models do it. So as we've done for decades, sort of like the pseudo global warming kinds of experiments, you can do exactly the same thing with AI emulators, where you say, add plus 4K to your SSTs and put those into that emulator after it's been trained on, say, present day climate. This is, however, where we get into trouble. Well, there are lots of ways, but when we start thinking about out of sample, if you only trained on the present day and you start to do those sorts of experiments, you could run into problems. And that's where then this is now my sort of personal opinion, I think the future of this area is going to heavily rely on some of our dynamical physics models as training sets. I think for myself, that will be an important way to start to feel comfortable when we get to those extreme tails and get to those climates and states and those impossible situations that have never happened before.
And I suppose it's then important to train it on multiple models with different climate sensitivities. Yeah. Okay. So let me ask a second question that came in on Slido that is somewhat related, and it may have the same answer, but I want to make sure we covered it. So carrying on the theme of unprecedented events such as the Pacific Northwest heat wave, so far outside of the range of events. Again, would an ML-based approach then train itself on a GCM data set to be able to capture these events that are unprecedented in the historical record?
Do you want me to answer this one too?
Anyone, yeah.
I can. So in wondering, aren't extremes sort of already outside of the testing sample? It sounds like what's being asked, right? So I think there are a few approaches. First of all, at least deep learning is regression. And so there are quite a few cases where if you don't go too far outside of your training set, actually fitting a line isn't a bad prediction. So there has been some success where at least I thought maybe there would be failure. And it turns out just because regression and lines are good approximations if you're close enough to your starting point. Another thing, as you pointed out, James, is I really think that training on climate models, if they themselves can do these extreme events well, is one way forward. And then a third one, and this is, we don't have time to really talk in detail, but the computer science community has a lot of applications where they only have a few samples. And so there are a whole suite of methods and approaches called like one-shot training and zero-shot training, which implies you have one sample of the event you are trying to predict. And they can be successful at that. And so it could be we need to start relying more heavily on some of these other approaches that are being used outside of, say, climate and atmospheric science to really get at what we're talking about, the gray swan or the impossible situations. Okay.
Sonia, please.
Yeah, so I think there is a great work we can do with emulators and machine learning. I think the Pacific Northwest heat wave event might be the one where you really need a dynamic model. So we had a study that was led by Dominique Schumacher in which we investigated this event. And I've seen actually another paper later on came also to similar conclusion. I think this event was really a compound event because we had three elements that were really extremes that kind of compounded together. So there was, on the one hand, the circulation was totally anomalous. That was mentioned also by Tim, I believe. And then in addition to this, we had super dry soils at the beginning of the event, which also contributed about 1/4 of the anomaly. And what we found was that there was an additional warming contribution from actually air from the ocean. So there was also basically an area in the ocean which was much warmer, which contributed moisture. And then when this moisture condensated, it provided additional heating. So you had three factors contributing to this event, which combined for this single kind of event. So I think we might still have some of those events which are kind of surprising us. And there, of course, it's really useful to have physical models to investigate.
Mm-hmm. Yeah. Isla, please.
Yeah, I just wanted to mention some methods that have been used to try and capture these events that at first appearance seem to be outside of what the models are capable of doing, like the Pacific Northwest one. So there's these ensemble boosting approaches that Eric Fisher has a paper where you kind of set the model up to have a heat wave and then produce many heat waves, and the models can produce magnitude of events like that event. And then Karen McKinnon has a paper about kind of exploiting the characteristics of the distribution like skewness and kurtosis. And even if the models don't produce a heat wave in the Pacific Northwest, if you take kind of similar regions in other parts of the world, they do happen. And then you can try and put constraints on their probabilities that way.
Yeah, great point. Thanks. Okay, so yeah, continuing this theme of novel modeling approaches, I wanted to ask about hybrid approaches. So combinations of, say, ML models and process-based models, GCMs. I just wanted to get a sense of where we are at with the state of the science of combining models to improve fidelity of our modeling. Is it the case that this is very early days, or is it the case that we have established methods that are ready for prime time attribution applications? What can we expect over the next 5 or 10 years? I'll throw that open. Isla.
I can just say what's happening from the CSM perspective is that right now we're developing just the regular version of CESM, but the next step after that will be a machine learning enhanced version of CESM where maybe some like machine learning approaches are used to optimize parameters within parameterizations, and maybe some actual parameterizations will be switched out. I think exactly what it's going to look like is not determined yet, but that's kind of the next thing that's planned.
Interesting. So so that would be to speed up CESM. Would it also improve the process-based representation?
I'm not sure that it would speed up CESM, but it would be kind of like trying to optimize certain parameter choices and parameterizations to try and improve it. So the hope would be that it would be improved through the use of machine learning.
Right. Oh, good stuff. Noah.
Yeah, I'm certain that in the next 5 or 10 years on that timescale, we'll see increasing use of machine learning as a bridge between global large ensembles at the resolution at which the modeling centers can afford to run large ensembles, and the global convection permitting models, as well as the kind of nested model frameworks that Ruby and others have shown. And I think there's a lot of potential to learn from the higher resolution simulations and then bridge to the large ensembles.
Mm-hmm. Yeah. Ruby.
Yeah, I think combining different approaches, including like physics-based high resolution model as well as machine learning model, is probably quite important for several different reasons. Number one, I mean, especially for high resolution model, is really, really difficult to calibrate. We don't actually know that the model is necessarily bad unless we really put in efforts in better calibrating the models. So in that sense, I think machine learning can be actually quite helpful in making sure that we are not missing something in the models that we can really get the best skill out of. And then secondly, of course, it's also very important that when we talk about using emulators or things like that, I think Libby already mentioned, we need to produce the training data for the emulators using physics-based model for different climate and things like that. So I think that is a very important part, because otherwise it would be very difficult to show or to prove that the machine learning methods are necessarily capturing out of samples.
Mm-hmm. Yeah. Okay, thanks everyone. So we just heard about maybe what might be coming up in the next few years. How about the state of today's modeling and hybrid combinations of modeling approaches? You know, we heard in the past hour about the complexity needed to capture these complex scale interactions. Would anyone like to comment on the state of current modeling approaches for attribution research? And for example, I guess for some events, we may only need to get the large scales correct, or even just the thermodynamics. I guess I'm asking, have we crossed the fit for purpose threshold? Reinhard?
I'm thinking aloud about this, but it seems to go back to me to what both Sonia and Tim and others have mentioned, that it really depends on why are we doing this. So I think then it gets to a situation where we want to sort of operationalize attribution and come up with hard numbers that are then used in, I don't know, litigation or something. Then I can see that we currently have one model setup that we are confident that works. So for example, I know that models perform very differently for European blocking, for example. I also know that model biases are different in different parts of the world. So I think Peter has shown that heat wave and associated with southerly advection over Western Europe. So these are not well represented in CMIP models and the trends of that, whereas maybe in other parts of the world it works well. We've talked about the extreme extremes versus not so very extreme extremes. So it seems we have a lot of tools to do science, but I'm not sure we have tools to do this other pushing a button thing, doing it operationally.
Yeah. Any responses to that? Sonia, yes.
Yeah, no, so actually, no, it is an area that is being developed right now. So this idea to have real-time attribution, this is something that is being done. I mean, this has been done in part already by the World Weather Attribution community. Actually, we didn't mention them well, but I mean, we should say, I mean, they've been really pioneer in there to just develop like a framework that has been published and basically is being applied. Every time you have a new event or for a lot of new events, and it's not limited to that community. So I mentioned for the fire event in Los Angeles, there were 2 studies already. I mean, it's done by several studies, not yet peer reviewed, but it's because it's done by a lot of researchers. You have at least some type of control mechanism on the results. So one was from World Weather Attribution. The other one was from a group that's called Climameter. They are based in France. So actually we had a European project called XIDA, where we worked exactly on this about the kind of basically operational attribution. So it was working towards this idea. And also within the WCRP, we're also pushing for a new activity where you would have like a yearly retrospective on events. And yeah, I mean, this is more operational than the really science part, but it's also useful that maybe you have, ready information when you're asking this question. So you need science on different levels. This will be more the applied part of attribution science.
Yeah, thanks, Sonia. Yeah, we did hear from those 2 groups last week when we had an information gathering session on methods. So yeah, very nice work there. So we have about 5 minutes left. I'm going to move to a Slido question that came in from one of our committee members that is somewhat related to what we were just talking about, but I think it's a bit more direct or abrupt. Are there any specific event types or regions for which attribution is simply not feasible with today's capabilities? And if so, what constrains our ability to do so?
I can provide the answer that IPCC would provide. So I would say we have some events for which we say we have low confidence in attribution. This includes, we mentioned the tornadoes and some severe convective storms. And there some of the problem is also with the availability of data. So that, and also it's not only, you may have data, but you may have a sample bias that, you will have more records where people are living. And you have also a change in reporting over time. So you may have data, but it's not easy to overcome the bias in the data. So I would say I do expect with 5 or 10 years of more data and more interest in this, we might be able to address those once we have a better data basis.
Yeah, thanks, Sonia. So yeah, limitations of data. I was just reminded we have until 15 minutes past the hour, so we have 10 more minutes of free discussion. So Noah, please.
Yeah, I think something maybe a bit more esoteric answer, but I think something that is worthwhile for the committee to grapple with is the broad question of whether like single event attribution is even possible at all from a scientific point of view and kind of the philosophy of science. And there is literature that I've encountered in as not as a philosopher, but working on extreme event attribution, of that question of like what, and it gets back to the question of counterfactuals and from a scientific perspective of making a falsifiable prediction, can that be done for a single event? And I think it's clear the NAS, this is not the NAS's first report, so there's some stipulation that this is possible, but I think it's worthwhile for the committee to spend some time grappling with that question.
Can you elaborate on that a bit more? What do you mean?
Yeah, so something's only happened once. And maybe this gets to Libby's point about the one-shot predictions also. But like if something's only happened once, is it possible for us to evaluate the attribution result compared with a counterfactual of global warming not having happened or aerosols not having happened, et cetera, for something that's only happened once in the real world? And again, I'm not a philosopher of science, but I would encourage the committee to engage a philosopher of science for that question.
I see. Thanks for that. Janice, I think I've missed you putting your hand up, so I'll let give you a chance.
I'm beginning to appreciate how easy my job is relative to all of you, modeling a phenomena in which I can test hypotheses. Did additional deadwood that could occur under global warming cause this fire? I can add it, I can take it away, I can see whether the phenomena is produced and how it's changed. That's a good way to test cause and effect hypotheses about what caused what. I think it's harder in continuous fluid dynamic systems where you can't really mess with Mother Nature and take away some components of the system. That was always much more difficult in terms of adjusting why a cloud system behaved the way it did. You have much fewer ways you can adjust it without stopping the simulation. Andy, did you have thoughts about that?
Yeah, it's always good to do rapid validation as well. Let's see. Thanks for that, Janice. Richard.
Yeah, back to the issue of where attribution is just not possible. So I think I tried to make that point that for places that are sensitive to changes in sea surface temperature in the equatorial Pacific Ocean, I would say that, yeah, you actually can't do attribution in using coupled systems. So East Africa would be one of those, or tropical cyclone distributions in the Pacific and the Atlantic. What the models have said should have happened over the last several decades is not what has happened. So I think that would draw into question attribution of any single event that sits within those decadal trends. If you use SST force models, they'll often perform better. But we have relatively few modeling groups keep SST force models up to date and distributed in near real time. And I think that we should urgently be persuading all climate modeling groups to run atmosphere models SST forced and release the data in near real time. That would greatly aid attribution, but that only gets it to, the atmosphere's response to the ocean. But ultimately, the problem with the attribution is how the patterns of sea surface temperature evolution, and the models just aren't getting that right. Forecast systems are also not getting it right because the biases creep in within the seasonal forecast. ECMWF have shown that recently, and some other groups as well.
And thanks for bringing up the point about accessibility of data and models. That's also a key need of modeling and ability of people to do modeling. I'm going to go to Ben next.
So just to poke at Noah's philosophical take, if models were perfect, you had an extremely rare event, one in all of lifetime. I don't know why you couldn't do the attribution to ask the question, does the probability of that event happening again increase or decrease? That within the context of, well, if our models were perfect. So I think our ability to do the attribution problem is limited by the quality of our attribution tools. I don't think it's limited by the philosophy of doing attribution. My take on it.
Mm-hmm. Yeah, thanks, Ben. Yeah. Gonna go to Sonia and then Tim. Sonia.
Yeah, so I have actually different points related to points that were brought up. So first about areas when it's not possible, I mentioned when there is no data, and I think Shad mentioned, yeah, when the models are failing. And again, there are several examples of this. There's this issue in the Southern Ocean, but there are also the issue with feedback to the carbon cycle. There are just areas where the models are failing. Obviously, there you cannot, and you need to improve the model, understand what is happening. About the more general question from Noah, so we have different ways, and I would also agree with what Ben just said. So assuming now you trust your model, and you have anyway two types of different methods for attribution. One is basically the probabilistic attribution. So you see your event as one member of a class of event, and you look at whether this class of events is becoming more frequent. So you're looking at change in probability of this class of events. So you're not trying to look at a single event, just as an event, as one example of a class of event. The other one where you look at a specific event is a storyline attribution approach, where you're actually simulating the specific event, and there you can actually switch off each of the different elements, actually exactly what Janice was saying. You can do this also with atmospheric models, because we can prescribe some moisture, for instance, to a climatological value. We can change the SST, we can change sea ice and so on to different elements, and look when you remove each one of those, how is this changing basically the event, and then you have to trust your model. And maybe on the more general question of philosophy of science, actually I got an email from Lisa Lloyd, who is listening to this session. So actually I had some exchange with Lisa Lloyd, who is a philosopher of science, and also with Naomi Oreskes, who is a historian of science, exactly on this question of attribution. How do you communicate about attribution? It's a field on itself, and maybe I would recommend the NASEM to also look into this question in a follow-up workshop.
Yeah, we'll certainly follow up on this point. Thanks for raising it, both of you. Yes, and I certainly agree. I think there's a lot more room to be more creative in combining models and tools to get over some of these data gaps and modeling gaps. Tim, did you have a comment?
Yeah, I had a comment, and well, just ask the panel if they had any thoughts about this. But one event, type of event, which we haven't talked about, and I guess it's either extremely difficult, potentially, well, no, not potentially impossible, but certainly extremely difficult, are cold events. So that's where, you know, the dynamics, if there is a dynamical signal, it's going in completely the opposite direction to the thermodynamic signal. So, you know, you sometimes hear, for example, when you, in the US, for example, you know, there's a big, what do you call it, polar vortex or something with the winds coming down. And some people say, oh, yeah, you know, that's because the Arctic ice has melted and the SST, you know, the pole to equator temperature gradient's reduced and the Rossby waves are stronger. And that's, you know, that's led to a big trough, which has led to cold weather. But, you know, I mean, whether we think the models are, I mean, that's really testing the dynamics to the absolute limit. And as I say, it's going in completely the opposite direction. I mean, storyline attribution, I mean, that's a good example, actually, where storyline would not help in the slightest, because it would tell you that there's no chance of it getting colder. but the dynamics there could be a signal of increased probability of cold weather if all this sort of Rossby wave stuff, is right, which I don't know actually. I'm not sure whether I believe it or not. But anyway, I just wondered what people think about that. Is that one thing that attribution science will not be able to say much about in the near future, or are our models getting good enough to say something?
Ben.
Ben, yeah, go on, Ben.
So I'm confused as to why you think it's not possible to ask whether the statistics of extreme colder outbreaks are going to change in a warming climate.
Sorry, no, I'm not saying that. I guess I'm asking the question, with the current generation of models with their various biases and things, do we think that's a feasible question?
Yeah. No. I would agree that I don't know if the models are of today's tools are capable of capturing that. But I don't think from the point of view, is it unknowable? That's where I would disagree. I think it's potentially knowable, just not today.
Yep.
Yeah.
Yeah, my understanding from Tiffany Shaw's presentation earlier was that it was possibly knowable. So, okay, I think we have 1 more minute left. So in the final minute, I'd just like to open it up and ask, does anyone have anything else they'd like to tell us about modeling that enables extreme event attribution that maybe we haven't brought up yet? We've gone from small scale to large scale, back down to small scale, coupled. We said something about aerosols, seems to be key. That's some forcing. Noah.
Yeah, well, just on the aerosol point, I mean, aerosols are one of many other forcings that matter at the scales of which these extreme events occur. So, obviously, land use, land cover change, the regional local hydrocycle, including human modification via irrigation and urbanization. So I think that aerosols are one word to describe the whole category of other factors in addition to anthropogenic greenhouse gas emissions.
Final word from Andreas.
Yeah, maybe just bring up tipping points, because tipping points could really bring us in a completely different regime. And then it's getting really difficult.
On that note, oh, sorry, Sonia, we'll have to close. On that note, we'll bring the panel to an end. You've given us lots to think about. It's been a fantastic discussion. So thanks very much to all our speakers for your time today. And I'll hand back to our chair, Jim.
All right, thank you, James. And it's not very often that I can honestly say a 3-hour and 15-minute Zoom meeting went by quickly, but in this case it did. Even if Noah and others have given us more philosophical questions to consider as part of our charge. Seriously, what I'd like to do on behalf of the full committee is to thank all of our speakers and panelists today for these great sort of flash talks. Very challenging to give a talk in only 5 minutes, but they were excellent. And the discussion was great as well. The committee, I really believe, obtained a lot of really useful information that we will consider. I know that I will go back and watch this recording and pick up even more. So I really want to thank all of the speakers and the panelists today, as well as our committee members, Tim and Nicole and James, for moderating these discussions. Just a small warning, all of the speakers are not totally off the hook. If the committee still has some lingering questions or comes up with some new questions, we might well reach you via email and ask some additional thoughts. So in closing, on behalf of the full Academy committee, I wish to thank everyone for joining our meeting today. And I look forward to our next information gathering session on impact attribution in Irvine, California on the 1st and 2nd of April. Thank you all so much, And have a great day, everybody. Bye.
Bye.